Okay, I think we'll begin this afternoon session. This session is more of a historical session related to people who were at King's and what they did here. Our first speaker is David Robinson. He came to King's in 1970, and actually I can remember coming here from Imperial to attend his excellent lectures on manifolds. David pioneered the subject of the uniqueness of solutions in string theory, and he's going to talk on gravity at King's, a brief history.
I'd like to thank Peter and George for inviting me to give this talk. This is a talk about people and old physics. There's not going to be any new physics in it. And what I intend to do is just quickly zoom through some of the work that's been done on gravity at King's or by people associated with King's. So there'll be a lot of other work done, important work done by other people, which I won't mention, and my apologies to them in advance. So I'll quickly have a look at what happened in the 19th century here, just to set the setting for the college, and then a brief discussion of the period 1918 to 1950. Then I'll talk about the Bondi era, and here I'll probably cover some of the same ground as covered yesterday by Daniel and by Dr. this morning. So there'll be some overlap, but looking at things slightly differently. And then finally, I'll take a canter through the last period, 1970 to 1985. So that's about 30 years ago, which is about the period that the British government sees fit to release some of its papers as being historical. It's a good point to stop. So just a quick resume of the college's background. The college was inaugurated in 1828 by a fairly reactionary group of people in reaction to the recently established University College of London, which is up the road, which is an avowedly secular institution. The first professor of mathematics was appointed in 1830. All the college calendars proudly indicate that there's something Wrangler and so on and so forth. You don't know what that means. Wrangler means you got first class honours in mathematics, and they ordered the list, so you were fifth down the list. So I think this was to show that they were getting reasonable people. And then the first professor of natural and experimental philosophy was appointed in 1826. He quickly got Wheatstone in as experimental philosophy person, and he remained as a professor of natural philosophy, which is the old term for physics, and all that was recounted in centenary history of the college and a history written after 150 years. Neither of these people was particularly distinguished. However, the college was very fortunate to appoint a very distinguished physicist in 1860, and it appointed him at a time when a period of 5 years, which was really his greatest period of original productivity, James Clerk Maxwell, was appointed at 29. And his time at King's has been recounted in an article, an interesting article by Silverberg, who used to be in the physics department here. What has Maxwell got to do with gravity? Well, we know Maxwell has to do a lot with electromagnetic waves, identification of waves and light. But at the end of his great paper of 1864, which wrapped up his approach to electromagnetism, he had a very short final section devoted to gravity, because of course he had noticed that electrostatics and had similarities to gravity in the case where bodies were similarly charged, but of course there was the problem that in electromagnetism, positive charges, for example, repel, whereas in gravity, massive bodies attract. And he tried to resolve this problem, first of all, by considering how one interprets attraction and repulsion in terms of the field. He wanted a field theory of gravity. So he thought, well, in the case of, let's say, the case of two positively charged bodies, what does repulsion mean? It means that the energy density is maximized when they're coincident and diminishes. This is the local energy density as they move apart. So diminishing intensity of the field energy was associated with repulsion and the converse for attraction. So how to do this with gravity? And the only way he could think to do it was to associate a negative intrinsic field energy with massive bodies, but have an ambient positive energy, which is always sufficiently great so that the energy density was always locally positive. And the problem with the existence of this ambient energy made him finish his paper, and the last sentence in it. As I'm unable to understand in what way a medium can possess such properties, I cannot go further in this direction in searching for the cause of gravitation. So the problem of energy has been a significant one in gravity from those days. The other person from the 19th century I want to mention is William Kingdon Clifford. He was a student here in the junior department that this place ran as a school and a college from 1860 to 63. Of course, he was an outstanding student. He was won prizes in mathematics, classics, English literature, and also gymnastics, of all things. And he's remembered, of course, in the context of gravity for his brief, very brief, one-page note that he wrote when he was at Cambridge in 1876, where he made a number of comments, having translated Riemann's work into English. He made these comments about gravity, and they seem retrospectively to be prescient. In particular, this property of being curved or distorted is continually being passed on from one portion of space to another after the manner of a wave. And the variation of curvature of space is what really happens in that phenomenon, which is called the motion of matter, whether ponderable or ethereal. So I don't think one should read too much into it because this is all he said, but in the light of the development of Einstein's theory, it's curiously future-looking. Fast forward to the period of general relativity, the period starting just after the First World War. And I thought I'd start this period off by just noting that the major event probably of this period was Einstein's visit to King's in 1921. He was invited by Viscount Haldane, who's on the left there, with Einstein and his wife at King's. He arranged for Einstein to visit England, and he acted as host. Einstein first of all spoke up at Manchester on gravity and geometry, and then he spoke at King's, actually it was on June the 13th, not the 10th. Einstein's visit is described in some links in Ronald Clark's biography of Einstein. And what did Einstein speak about? Well, he really spoke about the general nature of the theory. The title of the talk was The Development and the Present Position of the Theory of Relativity. He spoke in German for an hour to a rapt audience. All this was vastly publicized in the newspapers, and he started off, this was just after the First World War, by really being very tactful about the state here, and of course because of its relationship to Germany at that time. It's a special joy for me to be able to speak in the capital of the country from where the most important basic ideas of theoretical physics were brought into the world. So you can see that he's trying to be extremely complementary. I think of the theories of motion of masses and gravitation which Newton gave us, and of the concept of the electromagnetic field by Faraday and Maxwell, which provides physics with a new foundation. One may well say that the theory of relativity brought a kind of conclusion to Maxwell and Lorentz's grand framework of ideas by trying to extend the physics of fields to all their phenomena, gravitation included. And one of the main points that Einstein tried to make in this talk was that the subject was an experimental subject. It wasn't a matter of philosophy. Now, in this period that I'm talking about, there was a certain amount of research done in gravity at King's. But most of the people doing it were otherwise occupied. They do a bit of relativity, but they do a bit of other things. And I would make no claims that there were any huge advances made at King's in that time. So most of these people were in the mathematics department. Wilson was in the physics department. Only one of them, George McVitie, who was a cosmologist, was primarily engaged in relativistic research. But let me just say a little bit about each of these people. In fact, the first research paper in GR at King's appears, as far as I can tell, to have been written by William Wilson, who was in the physics department. He's the Wilson of the Wilson-Sommerfeld quantization condition in the old quantum theory. And his paper was published in 1918. Today, it doesn't seem terribly significant, but I suppose at the time it was in advance. The motion of the particle in the gravitational field is treated from the point of view of the general theory of relativity. It's shown that equations of motion can be expressed in Hamiltonian form. And he also included a short outline of the Minkowski theory of relativity as he called it. So the work here in GR dates at least from 1918. Somewhat more substantial, or at least currently substantial, work was done by George Jeffrey, who was the sixth professor of mathematics. He was here between 1922 and 24. He came from University College London and then went back to UCL. Did really two main things. He co-authored the English translation of the collection of the early papers on relativity with a preface by Sommerfeld. Some of you may have seen it. It's a Dover edition, and it's still available and still used, actually. But the other thing he did, and this was after he moved back to UCL, he co-authored with O.R. Baldwin the first investigation into solutions of the Einstein-Maxwell equations. It's interesting to see the background that this paper had. When you look at the references, they're few and far between, mainly to Eddington's 1922 paper, but also to Lyell's book. So there's very little previous work referred to, and it deals in part with the question, the matter raised by Einstein when he wrote his first paper, that what was the nature of waves, were they longitudinal, transverse, or transverse. And they investigated all the three cases. They showed that the first two were flat by doing what one would do these days, calculating the Riemann tensor and showing it zero. And then they investigated transverse waves, which had metrics of this form, where A, B, and C were just functions of t minus z only. And they computed effectively the solutions and noted that they had coordinate singularities, and their conclusion was that really to deal with waves in GR, you had to deal with diverging waves. They put their coordinate singularities down, at least it seems to me, maybe I'm reading between the lines, due to the fact that they were dealing with wavefronts of infinite extent. So plane waves King's begins there. The next two people were here mainly in the 30s, which was really a rather low point indeed for relativity. Both of them, of course, had their careers here interrupted by the Second World War, when the college was moved to Bristol, the medics went to Glasgow, and they were both heavily involved in that. George Temple, in the early days, wrote a little bit about Whitehead's theory of gravity. That was a theory of gravity which was attractive at the time, around about 1922, because apparently for some philosophical reasons, but also because it was a halfway house between special relativity and general relativity. So it was something that people who had managed to, by that point, to cope with special relativity felt more comfortable with, and it had the same sort of predictions as GR. This turned out to be, as was noted by Eddington, in fact, first of all, because the two theories both admitted a Schwarzschild solution as a solution. And this is a dead theory. There's an amusing, fairly recent paper by Will and Barry Gibbons entitled The Multiple Deaths of Whitehead's Theory. But he also worked on aerodynamics, quantum mechanics, analysis, and the history of mathematics. So he did a lot of other things. The aerodynamics was because during the Second World War he went to Farnborough, where he was involved in tests for aircraft and so on. After retirement from Oxford, and I guess that's what Oxford does to you, he became a monk. One person who was substantially involved in relativistic investigations in this period was George McVitie. He was a cosmologist. His period here was also interrupted, of course, by the Second World War, where he went to head the meteorology division in Bletchley Park. He knew nothing about it. He invented this division himself and stayed there during the Second World War. But he was a fairly forthright character, which didn't always go down too well. He wasn't very happy with the steady state model, and he was one of the few people in that period who consistently maintained the importance of the cosmological constant in cosmological investigation. One of his works actually has recently become of interest again in terms of black holes in spacetimes with non-zero cosmological constants. It's being looked into currently. After King's, he went and founded the department at Queen Mary College and went off to the States. So that brings me now to what is probably the main period of general relativity at King's. So it's what I call the Bondi era. And I think it's fair enough to call it the Bondi era because Bondi was the engine driving things. He was here from 1954 to 1971, and shortly after his arrival, he brought Felix Pirani over to join him, and Clive Kilmister. There's a picture of Felix when he was in his 20s, 1959, absolutely one. Okay, and Clive Kilmister in the centre there. Clive won't feature very much in what I say because he was a bit like Kendall. He did a lot of things. Relativity was just one of his interests, and he really wasn't involved in the gravitational wave saga, which I'll talk about mainly now. So that covers what I've just said. Bondi was the 10th professor of mathematics, and he really created a highly influential and productive work. And one of the reasons why they were highly influential was they got financial support from the United States Air Force, and that made a huge difference. They spent the money very well. They invited a huge number of people, virtually everybody in relativity passed through King's at that time, and some for quite long periods. So it was a major centre of activity. And the history of the support for general relativity by the Air Force has been written up by Josh Goldberg, who was the administrator of the grants at that time. Now, to come to the work on gravitational waves, we heard yesterday in detail a very interesting discussion of some of the background, so just let me remind you of the key features, roughly speaking. The investigation of gravitational waves begins possibly in 1916 with Einstein looking at the linearized equations. 1918 papers where he corrected some errors and so on. Applied the quadrupole formula. Eddington then corrected, he got it wrong by a factor of half. Eddington corrected the quadrupole formula. 1936, Einstein and Rosen published a gravitational wave solution. We heard the story of that yesterday, how it eventually came out as a paper on cylindrical waves due to the intervention of Robertson. Nathan Rosen actually was in the Soviet Union when Einstein published the revised paper, and I don't think he was totally pleased with the revision, because in 1937 he claimed, he went back to the gravitational wave solution and claimed there were no plane waves. Anyway, it was very confusing, and doubts about the gravitational wave's existence continued to be expressed by Einstein and Rosen, Leopold Linfield and so on for many years. And all the early work, such as work of Beck, Brickman, Baldwin and Jeffrey on exact wave solutions, appears to have been forgotten. So there was this confusion, and Daniel Kanefek spoke about it yesterday, and he's written about it in detail in his book. So this was the background to this period, in this aspect of research at King's. Basically, one can take the Bern Conference of 1955, celebrating the 50th anniversary of Einstein's special relativity, as the beginning of the work here. But it was attended by Bondi and Pirani. It was mainly the older people who were there. There were very few young people. In fact, Stanley Dazer of ADM and other fames told me that at a time he was on leave in Copenhagen, so he went to the conference and he saw this fellow in an Italian suit, so he went up and started talking to him and what Italian he had, and this person replied back to him what Italian he had, and eventually it realised that they were both better off speaking in English, and that was Felix Pirani. But there were just a couple of the young people there. But one of the important things was that Marcus Fehr told Bondi that there was this confusion in the state of gravitational radiation, and that Bondi was the guy to sort it out. Now, Bondi was just coming to King's. The department was small, it was only 10 people. He was only going to have a small group, and he was looking for a suitable topic for such a situation. So he thought, I'll go on to gravitational radiation, gravitational waves. In 1954, Pirani had finished his second PhD with Bondi in Cambridge and gone to Dublin. There's this curious thing. Felix Pirani had a PhD from Carnegie Tech, which he got with Alfred Shield. Then he went on a postdoc. Canadians paid had a postdoc at Cambridge with Bondi, and Bondi said, oh, well, since you're here, you might as well do a PhD as well. So Pirani ended up with 2 PhDs, and Bondi himself didn't have a PhD. So between them, it was one each, I suppose. So after his PhD, in the period 1954-55, he went to Dublin on a postdoc with J.L. Singh and the others there, and he started to think and work on topics related to radiation independently. Then they got together and I suppose reinforced Bondi's determination to pursue waves and radiation. For a long time, Bondi had doubts. Bondi's thinking was very Newtonian. His strength was differential equations. His thinking tended to be very Newtonian. He had astrophysical background, and that was appropriate. On the other hand, Pirani never doubted the existence of gravitational waves, as most of the younger people didn't. And he also thought, of course, that, as many people did at that time, that an understanding of the radiation field would be important in quantizing the field. At Dublin, Pirani Pirani was very much influenced by Singh. Singh was not only a general relativist, but he was a differential geometer of the first order. Singh had worked on the equation of geodesic deviation some years previously from a mathematical point of view. So he was really a very good person for Felix to be with at that time. And he started writing this paper, which came out on the physical significance of the Riemann tensor, which came out in 1956. And he starts the paper by saying, a difficulty in general relativity theory is the lack of what might be called a theory of measurement. One learns that all coordinate systems are equivalent to one another, but one does not learn systematically how to choose the appropriate coordinate system in which to calculate this or that quantity. Coordinate systems are usually chosen for mathematical convenience, not for physical appropriateness. This would not matter if calculations were already carried out in independent of the coordinate system. But this is not the case. The result is fruitless controversy like that over the harmonic coordinate system. And you could have said like that over gravitational waves. Now, what did he do in this paper, which was comparatively new? He assigned to each observer an orthonormal tetrad. Okay, so they had a locally Minkowski tetrad in which to make their observations, to make their physical measurements. And then he used the equation of geodesic deviation, sort of wave going through, or a cloud of test particles being in a curved space of time. He used the equation of geodesic deviation in cloud of test particles and showed that an observer using those can determine the full curvature tensor in the vicinity of the world line. So this was his attempt at an operational method of computing the curvature tensor. He compared this, and he did a few other things, compared this with the measurement of relative accelerations of tidal forces in Newtonian theory. So he made the analogy between calculation of tidal forces in Newtonian theory and the use of the geodesic deviation to compute the Riemann tensor. And of course, this has become very standard since. And he also considered spinning test particles and discontinuities in the Riemann tensor caused by waves. Just after he'd come to King's, Bondi and Pirani went off to the Chapel Hill workshop. Now, when you read the proceedings of the Bern conference and you read the proceedings of the Chapel Hill workshop 2 years later, there's a vast difference. The Bern workshop seems like the end of an era, like a memorializing the end of an era. This seems like the beginning of an era. There were young people there. Guido took along all his graduate students with the intention of making an impact, which he and they did. And it was the beginning of really modern GR. Now, Felix's talk dealt with essentially the paper I just mentioned. It's just a one-page contribution, but it made a really quite significant impact. Peter Saulson, a long-time member of the LIGO consortium, has written in this paper here, which discusses in detail the gravitational wave radiation discussions from the point of view of an observer. Nowhere in this one-page presentation are gravitational waves mentioned specifically, and that's true, but it must have been clear to everyone that applying this idea to the gravitational wave question would be one of its most important results. The discussion immediately following this paper makes this obvious. And in this paper, it also traces the influences of this paper on the LIGO experiment. But in the discussion following Pirani's talk, Bondi asked, can one construct in this way an absorber for gravitational energy by inserting an absorption term to learn what part of the Riemann tensor would be the energy-producing one? Because it is that part we want to isolate to study gravitational waves. I was interested yesterday when Daniel said Bondi had a more rigorous approach than perhaps some other people. I think it was rigorous in thought, but not in mathematics. When you read Bondi's papers, they really have almost an engineering attitude to them. Felix's response was, I have not put in an absorption term, but I have put in a spring. You can invent a system with such a term quite easily. So they're already thinking about the transfer of energy. And in fact, one of Felix's students, Peter Zeckerish, developed this idea later into gravitational compass. Richard Feynman was also at the workshop, and he heard of, I don't think he was actually at it, he heard of Felix's talk, and while he was there, being very quick, he developed a thought experiment to show the physical effects of waves, that is, that the waves could transfer heat to a body virtually by friction, particles moving with relative acceleration, according to the equation of geophysics deviation. This became called the sticky bead argument, and it's listed in an appendix to the proceedings of the workshop, which has now been published. It's interesting because it not only contains the talk, but it contains the discussions that follow the talk. In 1957, Felix Pirani was well established at King's, but he was continuing to think along lines which he had developed in Dublin. While in Dublin, he had proofread Singh's book on special relativity, and that contained an unusual algebraic and geometric approach to gravitational waves, where plane waves were interpreted in terms of the algebraic structure of the Maxwell field. So he was familiar with that point of view. He reviewed a paper, Singh got him reviewing for Maths Reviews. He reviewed a paper on gravitational waves by McVitie, which was really totally confused. It was a fairly sharp review when you read it. He says McVitie proposes one idea for gravitational waves and then has to reject it because it doesn't work and so on and so forth. And there's no invariant formulation of gravitational waves, and he hung on to this idea. And then the third bit of input was that he happened across a review, I guess probably in mathematical reviews again, by the Soviet physicist, a review of a paper by the Soviet physicist Petrov on the algebraic classification of the Weyl tensor. He didn't read the paper. He had it translated rather badly, he said, for him later, but he just read the review. But these things all clicked, okay, and that led to this paper, his 1957 paper, the invariant formulation of gravitational radiation theory. He told me once that he offered to have Bondi's name on this paper because they were obviously discussing it a lot. But Bondi said no, and I think quite rightly, when you read the paper, you see that it's not Bondi, it's Felix Pirani. And his main line of attack was indicated in the introduction. The investigation of gravitational radiation and general relativity is hampered by the lack of an invariant definition of that concept. And this is the point he hung on to again and again. An invariant definition is proposed in this paper. This definition is given in terms of the Riemann tensor. Okay. And in this paper, one of the consequences, one of the important consequences, was that he introduced English-speaking readers to the classification of the Weyl tensor into canonical types by Petrov. Subsequently, this classification was used in the proof of many interesting new mathematical results and in the finding of new exact solutions. For example, when you look at Roy Kerr's paper on the Kerr black hole, it's not called the Kerr black hole, obviously. It's called gravitational field of a spinning mass, which it was, and as an example of algebraically special metrics. So this line of approach influenced a lot of people. Petrov didn't get it quite right. Roger Penrose corrected it later. But it was right enough for Felix's purposes. The upshot of it was that Felix proposed that gravitational radiation was present if the Riemann tensor was algebraically special. That wasn't quite right, but it was in the right direction. Meantime, Bondi was pursuing the plane wave problem, and in 1957 he whipped off a paper to Nature. One sometimes had the feeling that Bondi would do a calculation and whip off the paper to Nature and then think about it a bit more. And in it, he starts off that paper by recounting a little of the history of the search for plane gravitational wave solutions of Einstein's equation. And in a way, it's a little bit of a mea culpa. He says that he and Scheidricker, who was a student of Infield, have both expressed the opinion that there might be no energy carrying gravitational waves at all in theory. And in this paper, he says this is not the case. Okay, they find the solution, and they show that these waves carry energy. That is the so-called sticky bead argument. At that time, when he published this paper, I don't think he realised that plane wave metrics had in fact been found, albeit in a fairly mathematical context. So I'm not surprised that they weren't all known by Brinkman. Not quite sure when. The speaker this morning said 1918. I thought we tried to conclude it early on. So Bondi at that point had indicated that he believed in plane gravitational waves. They had no coordinate singularities, and they transmitted energy. In early 1958, Felix Pirani went to Warsaw, gave a talk about his paper saying that gravitational waves had to be algebraically special. Andre Troutman told him that wasn't quite right, and so he invited Troutman, who was at that time a graduate student looking for Leopold Infeld, come to London and give 5 lectures. These were mimeographed, widely circulated, and very influential. The lectures were mimeographed courtesy of the US Air Force, but at the last minute, Bondi and Pirani found that the US Air Force wasn't going to pay for Troutman because he came from a communist country. So Bondi had to hustle off and find some money, something which Bondi was evidently very good at doing. These lectures covered the following topics. A lot of them were on equations of motion, which the King's group never really went anywhere near. Difficult topic that you heard yesterday. But they also covered the question of boundary conditions and gravitational wave theory in the first lecture. And that's probably the one which had most impact on the King's group, although quite what the impact was is not clear. These lectures were discussed in detail in April in the talk here. That talk's now been written up by Pavel Nowalski and Denson Hill, and you can have a look at it if you want. It was also discussed this morning, so I won't repeat it at great length. But what was in lecture 1 in words, the lecture had a direct influence on the King's group. Troutman imposed conditions on the metric at a great distance from an isolated system, strong enough so that the system could be regarded as having finite total energy, but weak enough so that it could be regarded as emitting gravitational radiation. So Troutman put down some boundary conditions using asymptotically Minkowski coordinates. He generalized the Summerfeld radiation conditions that were the source of his conditions. First of all, for scalar fields of Minkowski space-time, and he generalized that to electromagnetism and general relativity. And then in his far-field analysis of gravitational radiation from bounded sources, he evaluated the energy amendment for such systems of infinity and showed that energy could only be radiated away. He also showed that asymptotically, the Riemann tensor was of Petrov type N. How much of this sunk in is not clear to me, but it's what Troutman did. After Troutman's visit, in this period, the Bondi group got going, and one of the things they did was produce a whole series of papers which were published in the Royal Society. The series was called Gravitational Waves of General Relativity, 1 to 14. The first 12 papers were really in this era. One was a follow-up to the plane wave paper by Bondi and Pirani in 1989, and finally it was terminated by contribution from outside Kings in 1995. And the first line listed here, Les Marder was Bondi's first student at King's. Julian Vandenberg was his second student. And I'll talk about a couple of these papers very briefly. Just quickly about the third paper, which is the follow-up paper to Bondi's nature, which was just mentioned. And then I'll talk about the Bondi-Vandenberg-Metzner paper, number 7. The conserved quantities that are mentioned at the end of Newman-Penrose constants. Okay, so just quickly, the plane wave paper. This is the follow-up to Bondi's letter. They worked by analogy with, I should mention it was done with Ivor Robinson of Robinson and Troutman, 3 authors. Robinson was at Liverpool at the time. First of all, they worked by analogy with electromagnetism, and you can see here Felix Pirani's influence by defining what was meant by a plane wave. They discussed carefully at what was meant by a plane wave, and they defined it in terms of a 5-dimensional group of symmetries, which is what the plane wave has in the Maxwell theory. And then they looked for solutions which had 5-dimensional group of isometries. Fortunately, Petrov had made a list of such things, and they were able to find these fairly easily. They realized that they were looking at Petrov type N. And then they looked specifically in some detail at metrics of the form that I've written there, where the coefficients of all functions are just one variable u, which is tau minus zeta. Okay, and they studied sandwich waves, that is, plane waves joined to flat space on each side. They could use the flat space as reference spaces in which to unambiguously say what was happening, and they matched the flat space to the curved space, plane wave space, piece of the sandwich, by using the Schnerowitz's matching conditions. And Schnerowitz had started to introduce global techniques into general relativity, and they were using that. And so they considered the effect of such a wave, flat space, sandwich, and then flat, putting on test particles. And by looking at the equation of geodesic deviation, they were able to show the effect unambiguously on these particles and showed how the particles carried energy. And so this paper, I think everybody agrees, ended the long-standing controversy about the nature of the singularities shown in such ways. There were no such singularities. You patch bits of spaces together, bits of the manifold together in the way that we do in modern differential geometry. These singularities previously obtained were all coordinate singularities, and real waves are devoid of any such ones. So that ended that. But what Bondi was really interested in was gravitational waves from isolated source. And this is covered in this paper number 7 by Bondi, his student, Vandenberg, and A.W.K. Metzner. For calculation convenience, to see their way through the massive stuff, they dealt with actually and reflection symmetric systems. These symmetries were dropped, assumptions were dropped by Ray Sachs in a paper following it. And I think at the time, and Chapman wrote this in 1956, there was general agreement that Bondi was the first to give a systematic treatment in quite general metrics describing the radiation from the bounded source. This paper is interesting because it's divided into sections with people's names attached to them, which is quite unusual in papers. First and last sections were written by, well, the whole paper was written by Bondi, but the first and last sections Bondi assigned to himself, and of course he wrote them all. The second section, where the field equations, the coordinates, the characteristic initial value problem, at least formally, was set up. All the calculation stuff was done by Bondi and Vandenberg. Vandenberg finished his PhD in 1959, and Bondi said to him, well, I've got an idea for dealing with gravitational waves. We'll use null coordinates. Can you stay over the summer and do it? He was then going off to a lecturing job at Liverpool. Vandenberg was. So Vandenberg sat in the coffee room and calculated the way using null coordinates, trying this set of variables and that set of variables until they fixed on some which would separate out the equations, enable them to get a handle on the equations. And they had done that by about the end of the year. At that point, Bondi set off a letter to nature. In the spring of 1960, Bondi went off to Cornell, and there was a student there who worked with Philip Morrison, Metzner, and Bondi got him to look at the permissible coordinate transformations which would preserve the boundary conditions that they were imposing on the metric. And this is the source of the Bondi, Metzner, Sachs group. Had a lot of trouble finding out who Metzner was. Nobody I spoke to at King's, other people like Ken Newman knew who he was, but he was this person at Cornell who later went into publishing. And then Bondi wrote the last section, which I think he probably regarded as the most important one, where he introduced the concept of the news function. The function gamma in the metric is where everything comes from, and in the asymptotic expansion they used, the leading term was a function of u and theta over r. And the time derivative of that function is called by Bondi the news function, and it determines the mass loss in the way that we heard about this morning. So Bondi identified this term by looking at as the mass, by looking at his metric for the static case. He observed that when you turned on the news function, when there was radiation, when the news function was turned off, let's say the metric was static, there was no radiation, and that the mass loss was positive. Then he said about this work in this particular section, section D, thus we have the central result of the paper. The mass of the system is constant if and only if there is no news, the time derivative of C. Mass decreases monotonically as long as the news continues. And the Riemann tensor has a 1 over R non-zero term if and only if the second time derivative of C vanishes. So Bondi clearly regarded that as an important part of the paper. So I think there is some claim to say that this was the first clear understanding of mass loss in general relativity. Not the first, but very clearly described. Other work done at King's at this time, Ray Sachs, as I've mentioned, just followed up. It looks as if the papers were done at the same time, but that's not the case. He came 1961 for a year on a postdoc, immediately generalized Bondi's work, and it's not fair to say it was just a generalization. It was a very sharply written, illuminating paper, dropping the symmetry assumptions, so it would also deal with rotating bodies. And then Josh Goldberg, who was here, who developed the Goldberg-Sachs theorem on Petrov types. Shortly after that, Roger Penrose was here at, on a postdoc, 61-63, and at Cambridge, before he came here, started to introduce spinner techniques to deal with these sort of calculations. That made everything tremendously much easier, it seems to me. Felix Pirani's initial reaction was, well, you know, why do things with two indices when you can do them with one? But he quickly changed his mind and became an expert and stuff. It just really simplified everything considerably. And he worked with Ted Newman on constructing the Newman-Penrose formalism. Bondi has a comment on that too. He has a comment that he was very happy that he just got his paper in first, because using very abstract and modern techniques, Newman and Penrose came along very shortly afterwards and did something similar. But I think the main contribution that Roger made while he was here was in developing his informal boundary techniques. And first of all, in his asymptotic properties of fields in space-time in the physical review letter, but also in a number of other publications while he was here. And this really marked the beginning of the development of use of conformal techniques to cleanly say and describe what was happening and describe what was happening in gravitational radiation. For example, it made it much easier for people to talk about incoming radiation and outgoing radiation as separate quantities. One could do calculations locally as if having a boundary rather than extension. And of course, it was the beginning of a period of new insights into horizons and the global causal structure. That was extremely important development. And as far as gravitational radiation is concerned, it sort of brought to an end this period, a very satisfying conclusion. The work that was done at King's at that time was essentially explained at the 1964 Brandeis lectures by Troutman, Pirani, and Bondi, and there's a textbook which is sort of the spirit of that time, written by Braid and Bruno. Moving on quickly to the next page, the next stage, 1970 to 1980, the focus changed to interest in black holes and quantum theory. Basically, three new people came to the department: myself, Paul Davies, and Bondi retired, at least formally from his position, was replaced by John Taylor in '71, and Peter West came too, and they provided the distinctive quantum field theory presence. And the three main research areas at the time were classical black holes. I worked on uniqueness theorems for black holes, quantum field theory in non-Minkowski spacetimes, which Paul and others were involved in, and then other aspects of quantum gravity, geometrical quantization, quantum field theory, supergravity. For this conference, I'll just talk a little bit about the first two. This is a picture of people outside the King's building, this building we're in now, in 1976. The front row, moving from the right, is mic'd up. There's Chris Isisham, a lot of his students. Third from the end is Steve Christensen. The second from the end at the back is Steve Fulling. Tim Bunch is next to him. It's me, behind Chris Isisham. Next to me was somebody whose hand over his mouth actually was smoking a cigar, Stanley Dazer, and at the end there is Paul Davies. So this was a part of the group that was at King's in the 70s. Let me talk first of all about, very quickly, because I'm running out of time, about black holes. After the 1930s, there was a hiatus in the development of what became known as relativistic astrophysics, but it picked up in the 60s with the discovery of quasars, pulsars, and theoretical developments leading to the serious study of black holes. And at a meeting here in 1967, Werner Israel from the University of Alberta, but he was at Dublin at the time, announced a remarkable first black hole uniqueness theorem. It was for static metrics, metrics of that form where the coefficients B and the through metric GAB are in the definition of time, and I'll talk a little bit about that in a moment. I've given the details in an introductory review of all the work that's been done on this area in that paper. Let me say this was, what I'm going to talk about now, was just the beginning of the saga, which goes on to the day. My interest was aroused in this by a conversation I had with Bob Grosh in the States. I wasn't around at the time I was in the States. And he was interested in this problem. And the thing that puzzled me was that in order to obtain his result, Israel had to assume a special coordinate system which was based on equipotential surfaces of V. So V was not only the coefficient of the T squared, but it was taken as a coordinate. And he proved the theorem in the standard way. You equate a divergence to something which is positive, and then integrate over the manifold, and then from the boundary conditions, you evaluate the divergence using Gauss's theorem, and then on these conditions, and from the positivity of the terms on the other side of the equality, you conclude some results. All these results follow that standard uniqueness theorem approach. Well, I was curious about this. It wasn't clear to me that this would hold if this assumption was made. It included assumption essentially that the horizon was spherically symmetric. Could you actually prove that such metrics in general, not just of this form, were confined to the Schwarzschild solution? And together with Henning Hagen and Hans-Jürgen Seifert, I was able to do that in the following period, basically in 1971. What we did was we just focused on the properties that a static metric would have if it was going to be Schwarzschild. And one of the distinctive things about Schwarzschild was that the 3 metric is conformally flat. Now, in 3 dimensions, there's a Coffin tensor which vanishes if the metric is conformally flat, and by multiplying it by itself, you can form a positive quantity and show that modulo some multiplying factors that's equal to divergence. So one has the type of expression one needs for a uniqueness theorem. One had to deal with the points where the gradient of the potential function v vanished, that is w is 0, but after a lot of complication we could do that, and later on I was able to give a much simpler truth. In the meantime, people have been looking at the stationary problem, in particular Brandon Carver for looking at rotating black holes, and Brandon has been able to reduce the problem and obtain a result using the linearized field equation. He's been able to take the problem, I'm saying it again. Brandon has been looking at the rotating stationary case. He managed to reduce the problem to essentially a problem not in geometry but differential equations for the Bauer-Papapetrou metric of that form, and he'd obtained a certain uniqueness result, generalization in a certain way of the Israel theorem. To do that, he used the linearized equation, which was essentially a no bifurcation result. Equations that one had to deal with were just the 2 equations and 2 unknowns, h and the potential for w, no just functions in rho and z, but they were highly nonlinear equations. And although Brandon managed to prove it using the linearized equation, it started to clear how one could generalize that to the full theory. In the meantime, Stephen Hawking had looked at the whole uniqueness problem from a 4-dimensional point of view, and had proven a theorem, proven in inverted commas, because people are still looking at this, that either the metric had to be static, in which case the Israel theorem would apply, or axisymmetric, in which case this metric would apply. So I was able to, I looked into these things, I was able to generalize Brandon's result, more complicated Einstein-Maxwell equations, just to get a feel for the equations. I recovered Carter's results using a Lagrangian framework, which eventually proved the right thing by other people to do. And then working still in Carter's framework, I was able to prove the uniqueness result for the full nonlinear equations. In a paper which I entitled Uniqueness of the Curved Black Hole. This is now called the, this whole area of work is now called the conjecture that the curved black hole is unique. But all our work was in the reduced form. The work in 4 dimensions was initiated really by Stephen Hawking. At the same time, and I will just really say who was involved in this, because the following talk by Larry Ford is going to deal with this. People were interested in quantum field theory and curved spacetimes. Why was this? Well, some work had been done previously, but in 1974, Stephen Hawking wrote a paper called Black Hole Explosions, ? And that was, of course, his famous black hole paper, and that exploded not only black holes, but also the work in this area, and the people at King's became very involved in it. Stephen Hawking, Paul Davies was the permanent person here. Stephen Hawking was here from 74 to 76. Steve Christian was here from 75 to 76, and Larry was here from 77 to 79. And Paul's students, Tim Bunch and Nick Birrell, were also centrally involved. So as were Chris Isham and Mike Duff, and during a whirlwind visit, Stanley Davies. All these people were heavily involved, and they produced a lot of papers, a lot of significant papers, which is still important. And here's a list of some of the things that he did. He was putting Davies' unreal effect, that is known as the unreal effect, moving mirror radiation, and the quantum field theory of the Sitter space, bunch Davies. In fact, all that work was done here. A lot of it was technical work dealing with computing regularization of the expectation value of the engineering. And all this work was written up. Most of this was written by Kings, by Nick Durrell and Paul Davies. Nick was a Paul student. This became for a while the Bible in the field. I don't know if it still is. Well, let me just conclude quickly by saying there are other things I haven't talked about. I haven't talked at all about cosmology. The second edition of Bondi's very influential cosmology book came out in 1962. But not much cosmology really was done in the periods that I've been talking about here at King's. I haven't talked at all about the work done by the people doing quantum gravity. Chris Isham was probably the world's expert at the time on quantum gravity, and Mike Duff on covariant quantization. Their work was described in the proceedings of the symposium that Hawking gave his famous black holes talk. And of course, later on, twistor theory, or in particular, twistor theory, twistor integrals were kept alive here at King's by Andrew Hodges and Stephen Huggett. Stephen gave some lectures here, which were written up with Paul Todd simultaneously was doing lectures at King's, an introduction to twistor theory, which is still used, and other things. Of course, people had other lives, and while Andrew was here, he was finishing off his book, famous book on Alan Turing, uniqueness. Bondi was becoming interested in gravitational collapse, but he was also becoming more and more of a civil servant. In 1966, he saved London. No exaggeration, he produced a report that actually got them going on the Thames barrier, located where it is now. Became the Director General of the European Space Organization in 1967, and finally resigned his appointment at King's in 1971, becoming the Chief Scientific Advisor to the Department of Defense and a lot of other important positions. He kept his professorship at King's until he became emeritus. I guess that helped him in dealing with the civil service in the Department of Defense. Felix Pirani retired in 1983. Guy Kilmister retired in 1984. 1985, King's merged with a number of other colleges of the University of London, and for a while became something called KQC, and so this whole story came to an end.
Thank you, David, for that very enlightening talk. We're a bit behind schedule, but we could take a question. No question? Okay, let us thank David again. Well, another important topic that was studied here at King's was quantum effects in curved space-time. And Larry Ford was here at that time, an important member of that group. And he's going to talk on negative energy and the quantum stress tensor.
Okay, well, thank you. And thank you to the organizers for the opportunity to be here. And since this is a conference on modern developments and the historical roots, I'm going to flip that around and talk first about the historical roots, and then my title will refer to some modern developments I'll get to in the second half of the talk. Okay, so as David indicated, King's was a hotbed in the 1970s of activity in quantum field theory and curved spacetime. But first, I just want to mention a few, and the fact that I think David mentioned some of these, some of the forerunner work. Quantum field theory and curved space-time. Though in particular, in the modern era, Leonard Parker was one of the first people to start seriously talking about that with his treatment in 1969 of particle creation in gravitational fields. Although in fact that actually, there was a much earlier paper 30 years before by Ernst Schrödinger who did quantization in the expanding universe and discovered what we would now call particle creation, although Schrödinger was very disturbed by it. He found that the solutions of a wave equation in the expanding universe didn't have pure positive frequency, but they got mixed. And in his paper, he refers to this as an alarming phenomenon. But of course, now we understand that it's actually something very interesting, is particle creation. And I think Parker's work was influential because it was certainly cited by Hawking in his paper on black holes, the idea that if an expanding universe can create particles, then perhaps a black hole could also create particles. And then, of course, the landmark paper of 1974, which is by Hawking, in fact, showed that. So now let's come to the slightly later in the 1970s, some of the work done. There was a great deal of work done in the mid and late 1970s here on various aspects of quantum field theory and curved spacetime. And of course, a lot of this was focused to better understanding the Hawking effect, understanding what's going on, how to understand the Hawking effect, in particular how to understand back reaction. Because if a black hole is going to create particles, then somehow the energy is being carried away. And how do we describe that carefully? And it was soon realized that that would require, first of all, definitions of a stress tensor in curved space-time, more precisely the expectation value of a stress tensor. And it would have to involve violations of classical energy conditions, that is the negative energy going down the black hole. And there were, of course, there were many other things, some of which I'll mention, one of which was the paper by Bunch and Davies on quantum field theory in de Sitter space. This wasn't the first paper about quantum field theory in de Sitter space. There have been other people write about that, but it happened to be fortunately written in a way that was especially useful when inflation was discovered, was first proposed by Alan Guth a few years later. That is the formulation that Bunch and Davies used led itself very naturally to talking about things like inflaton field fluctuations and during an inflationary phase. And so let me go on now to talk a little bit more about the expectation value of the quantum stress tensor operator. So of course, this is what you need if you want to have a semi-classical theory of gravity, where you couple a classical gravitational field to a quantum matter field, view the expectation value as the source. Of course, this isn't expected to be a complete theory, but it's in some sense a crucial transition from classical theory to quantum theory. In fact, any reasonable quantum theory of gravity should have this as a semi-classical limit. But there are several subtle issues with trying to define this expectation value, not the least of which is formally infinite. So it needs regularization and renormalization. And that was very actively pursued here at King's in the 70s, how to calculate the expectation value of the stress tensor. And one remarkable feature of it, which was also discovered here at King's, was the conformal anomaly. Namely, that if you start out with a classically conformally invariant field, like the electromagnetic field, in which the trace of the stress tensor classically is zero, when you renormalize the expectation value, you basically find that it develops a non-zero trace. And that was apparently first pointed out actually in a paper by Keffer and Duff, and then later in more detail by a paper by Dester, Duff, and Isham, which is written here at King's. And of course, the physical feature of the renormalized stress tensor is it typically will not have positive energy density. It will violate the energy conditions. And there was a very nice model given by Fulling and Davies, which was designed partly to understand black hole evaporation, but is very interesting in its own right, and it's a moving mirror model. So basically, in two space-time dimensions, a mirror is a point with Dirichlet boundary conditions. So you imagine you have a massless scalar field that has to satisfy the condition of being zero on this whirl line of this particle, but you let that particle accelerate. Then, in fact, you can calculate the radiation from it by considering the mapping of null rays that reflect off of the mirror. And there will be quantum radiation emitted to both sides of the mirror here, although I'll talk about the right side. So the basic ideas, in fact, follows very closely the construction in Stephen Hawking's 1974 paper on black hole evaporation. You consider an incoming ray of constant v coming in from infinity with constant v. It reflects off of the mirror and comes a constant u ray. And the crucial thing is the relation between the values of u and v. There's a function, either capital G of u or little g of v, which describes that. And if that function is a nonlinear function, then there's mixing of positive and negative frequencies. Because the mode function is a mixture of the incoming piece coming in from scri minus and the outgoing piece going out to scri plus. And then typically this, when you Fourier transform this, it will involve a mixture of positive and negative frequencies, which means the particle creation. So, in fact, what Fulling and Davies showed is that the mirror radiates a flux that's given by this formula up here. Very simple. Things are much simpler in 2 dimensions than there are in 4 dimensions. You don't have any angle meta barriers to worry about. So you can actually give a very simple closed form formula for the stress tensor, which you cannot do in 4 dimensions. But in terms of the mirror's velocity, the flux has this rather messy looking form. But if you look in the non-relativistic limit, the flux is just proportional to the acceleration. And the minus sign there indicates that if the acceleration is increasing to the right, then the mirror is radiating negative energy to the right. Of course, correspondingly, it's radiating positive energy to the left. So this is a simple example of negative energy in quantum field theory.
What is V is a speed, right? V is a speed.
Yeah, unfortunately, this V, I think the two V's have a slightly different shape, but it's bad notation. This one is speed, vx dt.
Since F is equal second derivative of speed,
That's right.
then it's derivative for second.
That's right. It's the rate of change. It's the rate of change of acceleration. Sorry, not rate of change. Yeah, if the rate of change of acceleration is positive, then on one side, then the mirror is radiating negative energy. That's right. And in fact, in this Fulling and Davies paper, they found a specific trajectory which emits thermal radiation. Essentially, it models the Hawking effect. It's given by this particular form right here with a constant kappa in it, which is, to make the analogy with black holes, you take to be the surface gravity of a black hole. And what they show is that in this case, there would be negative energy radiated to the left, positive energy to the right. If you analyze the spectrum of particles that go off to the right, it's a thermal Planckian spectrum of particles with this temperature. And in fact, it's essentially it's exactly the same transformation between the in and the out modes that would arise in a black hole space-time. So it's very close to a black hole. And in fact, you can carry the two-dimensional models a little bit further and make two-dimensional black hole space-time models and calculate, and in this case, you can calculate the stress tensor exactly in the two-dimensional space-time. And it gives you a rather nice picture of the back reaction. Namely, you get positive energy radiated out to scribe plots and negative energy radiated down the horizon, which exactly confirms your intuition about what a black hole should do. Of course, this was done by Fulling, Davies, and Unruh in 1976, while Fulling and Davies were at King's. Of course, this can be generalized to 4 dimensions, but is much more complicated. And in 4D, you get qualitatively the same picture, but the only way to handle the problem is by numerical computation, whereas the 2D model is a simple, analytically soluble problem. Okay, so now I want to turn and talk a little bit more generally about negative energy and why it's of interest. So, of course, negative energy necessarily is associated with a repulsive gravitational effect. After all, the Hawking effect of negative energy is what causes the black hole to lose mass. Because you violate the classical energy conditions, there's a possibility of evading the classical singularity theorems. And then you could also construct, say, exotic possibilities like the Morris-Thorne traversable wormholes, which are supposed to be tunnels between different regions of space-time. And those solutions require negative energy because basically light rays that go into this and initially focus have to at some point start to defocus. And for the Ricciardi equation, basically the only way you can get initially focusing rays to start turning around and defocus is to violate the classical energy condition, to have some negative energy that creates effectively a repulsive gravitational effect in here. And you can go even further. Miguel Cuvier showed how to construct a space-time that looks like a warp drive. That is a bubble that surfs across space-time faster than the speed of light, as seen by outside observers, and it necessarily requires negative energy. And of course, once you go faster than the speed of light, it's not too hard to modify things and create a time machine. That is to create closed time-like curves. And in fact, Hawking showed that if you want to actually build a time machine, you must have negative energy. Now, of course, there are examples of space-times like the Gödel universe that have closed time-like curves in them, but without negative energy, but those are eternal closed time-like curves. If you want to start a universe that didn't have any closed time-like curves and create them, you have to have negative energy to do that. And finally, there's another disturbing thing that you could do if you had large amounts of negative energy, and that's to violate the second law of thermodynamics. So the simple way is to imagine shining negative energy onto a hot object, such as a black hole or any other object, and basically reduce the mass of the horizon area without necessarily a corresponding increase in entropy someplace else. So of course, in the case of the black hole evaporation, the loss of entropy of the black hole is more than made up for by the entropy of the outgoing thermal radiation. But if you show negative energy on the object, there isn't any entropy generating someplace else. So you'd apparently violate the second law of thermodynamics. So of course, if you want, of course, Hawking was originally inspired by Jacob Bekenstein's work. Jacob, incidentally, was a fellow student of mine with John Wheeler's at Princeton. And Jacob was concerned with the question about what happens if you throw hot objects into a black hole. What happens to the entropy? that would appear to violate the second law of thermodynamics. If you throw your hot cup of coffee down a black hole, and Jacob decided that the resolution of that is to assign an entropy to the black hole itself. So its entropy will go up. And of course, that, interestingly enough, Stephen Hawking was critical of that idea initially. I think in 1962, he gave a talk at a conference criticizing Bekenstein's ideas. But then a couple of years later, he gave a talk at the same series of conferences admitting he was wrong, that in fact black holes do have a thermal character. So given how powerful the second law is, one suspects that the problem here is not with the second law of thermodynamics, but perhaps with too much negative energy. And that, in fact, was a question that I thought about while I was here at King's. And in fact, in 1978, I wrote the first paper on what later came to be called quantum inequalities, which were proposing that there are severe restrictions on the amount of negative energy that you can have. I mean, certainly we know that you can create states, even in Minkowski space, that have negative energy. But I propose that there are restrictions, and essentially an inverse relation between the magnitude and duration of the negative energy. And these inequalities have later been proven rigorously by a number of people. But they generally take the form of, take the energy density as seen on the world line of an inertial observer, sample it with some sampling function that has a characteristic width, then the sampled energy cannot be more negative than some quantity that scales inversely as 1 over tau naught to, say, the 4 in 4 dimensions. So that allows you to have negative energy, but it severely restricts what you can do with the negative energy. And I was able to show in my 1978 paper that if you have an inequality like this, then although you might get a small decrease in the entropy, momentary decrease in the entropy of the black hole, it wouldn't count as a macroscopic violation of the second law. And it would correspond effectively to a loss of less than 1 bit of information before the compensating positive energy comes and restores the effect.
So, well, you mean locally negative energy density?
Yes, negative energy density.
Negative energy density.
Yeah. When I say negative energy, I mean energy density. I just leave out the density. So here are some more precise formulations. So here, of course, this is the energy density. These are for flat space time. So in 2 dimensions, Aina Flanagan proved the bound of this form in terms of the sampling function. And this, incidentally, is the optimum bound. Aina was able to show that there existed a state which saturated this bound, so you cannot do any better than this. In 4 dimensions, the optimum bound isn't known, but one of the best bounds was given by Fuster and Eveson, I think about 1992, which has a slightly different form, but also basically, if you put in a specific sampling function with a given width, you'll get back to something like the result I had on the previous slide. It'd be basically like C, a constant divided by the sampling time squared in this case, or sampling time to the 4th power in that case. Okay, so now I want to move on to a little more recent work on stress tensor fluctuations. And we'll see how this is related to some of the things that I've talked about earlier in this talk. So let's consider again the Minkowski vacuum, where if we've normal ordered the stress tensor, the expectation value is 0. But the vacuum is not an eigenstate for the stress tensor operator. So that means that there must be fluctuations. That is, that the local energy density, if you made a measurement of the local energy density, you wouldn't necessarily get 0, but you would get some value that would have to average to 0 after repeated measurements. And of course, for the point of view of gravity, this leads to the very interesting consequence that there will be stresses and fluctuations that will cause space-time geometry fluctuations, what you might call passive. This, of course, is completely separate from the fluctuations that come from quantization of gravity, but quantum gravity has to also involve passive fluctuations that are driven by fluctuations of the stress tensor operator itself. And of course, in order to talk about this in a clear way, we need to have a probability distribution. So, and in fact, then in order to do this in a meaningful way, you have to average the operator over a finite space-time region, or at least over a finite amount of time. You can average along a whirl line of a finite time, or you can average in both space and time. And when you do that, if you start calculating the moments, that is the expectation values of the powers of the operator, you'll find that typically the odd moments are non-zero. So that means your probability distribution must be skewed and is hence a non-Gaussian function. And in fact, you can show that the probability distribution will always has to have a lower cutoff, at least for things like the energy density. For operators that are classically positive, such as the energy density, the probability distribution must have a strict lower bound. And furthermore, this strict lower bound is in fact the quantum inequality bound on any expectation value. And that follows because this lower bound is the lowest eigenvalue of this operator. Of course, we know from quantum mechanics that, that if an operator has a bounded spectrum and the lowest eigenvalue, that lowest eigenvalue is both the lowest expectation value you can ever create in any state, and is also the lowest value you can find when you're making measurements in any state that's not an eigenstate of the operator. In a sense, that's why where the quantum inequalities come from is that operators like energy density have a bounded spectrum. Okay, so one of the first results on the probability distribution was done a few years ago by Chris Fuster and Tom Roman and myself on a scalar field in 2 dimensions. We actually did it more generally for a general conformal field in our paper, but here I'll quote the case of the scalar field. And in this case, I won't go into the technical details, but we basically used something called the moment generating function and found a way to actually solve explicitly for the probability distribution in the special case of Gaussian averaged energy density. There are technical reasons that we had to use the Gaussian, and that's the only sampling function for which the exact solution of the probability distribution is known. But so the quantity we're going to deal with is the energy density of this massless scalar field averaged in time at a fixed point in space with a Gaussian that has a characteristic width tau. So of course the energy density in units where h bar and c are 1 has to have units of 1 over time squared. So the natural variable to use is energy density times time squared. That's a dimensionless variable. And you can ask then about the probability of finding different values of the energy as in terms of a probability distribution on x, the dimensionless energy density. So you're going to imagine now that you're going to have some device which is capable of measuring this Gaussian average energy density, and you'll do repeated measurements. Each measurement will give you a number, and then you're going to tabulate and plot these numbers. And you'll find something that looks a bit like this, which is really this function. Actually, that function has a name. It's called the shifted gamma distribution. Because it's essentially, it's the same function that appears inside the argument of the gamma function, an exponential times a power with rather funny looking numbers like the 23/24 that appear. So in fact, this distribution is actually singular, but it's integrally singular. So in fact, the integral of this function from minus 24 pi to infinity is in fact 1, despite the fact that it becomes formally singular near the lower bound. Of course, this lower bound is exactly Aina Flanagan's optimum lower bound, quantum inequality bound for Gaussian average energy density, as it should be, because it is the lower bound on expectation values. And this is, so of course what we're dealing here with is the probability of the vacuum state. I should say these are vacuum fluctuations. So we're in a two-dimensional theory in the vacuum state. We're going to imagine now that the vacuum state is not an eigenstate of average energy density. We're going to do repeated measurements of that energy density and find out what we get. And they claim that this is the result. And rather interestingly enough, if you calculate the area under the part of the curve that lies between the lower bound and 0, you find that counts for 89% of the probability, and only 11% for all of the rest of the curve. Unfortunately, the way it doesn't look like that, but there's a lot of area stuck up in here, in this little part where the thing is becoming integrally singular. So, in fact, in this idealized world, your repeated energy density measurements will give you a negative number 89% of the time. But the other 11% of the time, when you get a positive number, you tend to get a much bigger positive number. So they average to 0. So sometimes I like to make a wealth distribution analogy here. That is, most of us are down in this region, just a little bit in debt. But then there are a few people way out here that have vastly more, so that everything averages out to 0. Okay, well let's ask, what about 4 dimensions? Well, 4 dimensions is much harder. That is, it's much more difficult to construct define the probability distribution. But you can say some things about the distribution. So in particular, Chris Fuster and Tom Roma and I also looked at, in 4 dimensions, the Lorentzian sample energy density. And I should say a little bit about what we did. We took the so this is the energy density for various fields, such as the electromagnetic field. We did both massless scalar and electromagnetic fields. But since the electromagnetic field is more physical, let's focus on that. So we weren't able to calculate the probability distribution uniquely. But what we were able to do were to calculate various moments of the probability distribution using an algebraic computer program. Basically, Chris Fuster wrote a Maple program. And the reason for choosing the Lorentzian is that integrals of a Lorentzian can easily be done by contour integration. So we calculated something like the first 65 moments of the Lorentzian sampled energy density. Well, we did actually phi dot squared energy, and then scalar energy density and electromagnetic energy, and all those are related to one another. So we didn't have to calculate the moments separately for each object. And those, of course, not surprisingly, become huge numbers. If you want, if you look either on the supplemental material on the archive or the supplemental material in PhysRev D, you can actually see all those numbers if you want to, but they're not particularly. They're just huge rational numbers. But after computing those very large numbers, we were able to infer an asymptotic form to the probability distribution, which for the electromagnetic case, these are the numbers. It basically falls off rather remarkably like an exponential to the 1/3 power with weaker 1 over x squared. First there's a technical complication that I should tell you about. The moments here are growing like the nth, if you consider the nth moment, its value is growing essentially as the quantity 3n factorial as n increases. And there are theorems that is often the case that if you know all of the moments of a probability distribution, you can reconstruct the probability distribution. But there are restrictions on your ability to do that. And that's given by something called the Hamburger moment theorem. Now the Hamburger moment theorem basically says that the moment should not grow faster than n factorial in order to construct a unique probability distribution. If they grow faster than that, then in fact there can be more than one probability distribution that has exactly the same set of moments. And that's unfortunately the situation that we're in here, that we cannot say with certainty from the knowledge of the moments, even if we knew all of the moments exactly, we could not say for certainty what the probability distribution is. But based on other examples where there are two different probability distributions that have exactly the same moments, they tend to differ by oscillatory functions. If you think about it, that's essentially the only way that the very high moments can be the same, is if they're very rapidly oscillating functions. So essentially, if you're interested not so much in the fine details of the probability distribution, but things like the associated cumulative distribution, that is the probability of finding a value greater than a certain amount, then in fact these oscillations are not likely to be important. So we give at least some heuristic arguments that even though p of x is not uniquely determined in this case, its gross behavior, particularly this one exponential or 1/3 behavior, should be in fact well characterized by the rate of growth of the moments. Well, let me comment on this 1/3 power. This, of course, is a relatively slow fall off, much slower than an exponential. So it means that the probability of large fluctuations is relatively high. Unlike the two-dimensional case, where you recall in 2 dimensions, the formula I showed was something falling exponentially. So in particular, this means that if you look for large rare fluctuations, if you consider the system at finite temperature, at some point vacuum fluctuations will have to dominate over thermal fluctuations because the thermal fluctuations follow a Boltzmann distribution, which goes as an exponential of energy. The vacuum fluctuations are essentially going as an exponential, in this case, of a 1/3 power of the energy density. So that potentially will lead to some very interesting effects, which I'll talk about soon. But first, let me talk about some other, even more recent work that Chris and I have done, which are stress tensors measured in a finite time interval. So one of the problems of a function like a Gaussian or a Lorentzian is it has infinite tails into the future, but even worse, into the past. So they can't represent a real measurement because they have to represent something that started in the infinite past and then in addition is never completed. So it would be much better if the sampling functions that we're dealing with, so let's call it f of t now, were compactly supported. So a compactly supported function will be strictly 0 outside of a finite time interval. However, we still like it to be infinitely differentiable. There's a C infinity, clearly they're non-analytic, but a C infinity non-analytic function. And the Fourier transform of such a function necessarily falls more slowly than an exponential. Well, that's something that one can show. And in fact, we consider the case where the Fourier transform falls as the exponential of a fractional power. We'll call it alpha. So of course, alpha equals 1 is the Lorentzian, which is not compactly supported. But if you let this parameter alpha be less than 1, this does represent the Fourier transform of a class of compactly supported functions, which in coordinate space can be written as something called Fox-H functions, but that's not particularly important. So what we show, though, in this paper is that the asymptote, we basically again look at the rate of growth of the moments. We show that the rate of growth of the moments is related to the rate of fall off of the sampling function. And we basically showed that the rate of growth of the dimensionless sampled energy density will basically be governed by a formula which has the same functional form as you saw in the Lorentzian case a moment ago, but with a different fractional power, where C is alpha over 3. Now, of course, this includes the Lorentzian fortuitously as a special case. You see, the Lorentzian is not compactly supported, but it's a limit. So as you approach the Lorentzian, you get the 1/3 power. But if you have other functions in this class where alpha is less than 1, then you get even slower fall off. Alpha equals 1/2 is a possible choice for a compactly supported function. In fact, Chris Fuster found an electrical circuit, whose a very simple electrical circuit involving an inductor and a capacitor, such that when you flip the switch, the current rises according to a function that is alpha equals 1/2. And of course, that function then would be associated with probability falling like x to the an exponential of something to the 1/6 power. So, of course, the form of the switching function is very important, and the switching in a finite time interval can produce large fluctuations. So, in the last few minutes of this talk, I'm going to talk a little bit about some of the possibilities, possible effects. So, one which I've recently done with a student is the possibility effect of large stress fluctuations on barrier penetration. So of course, first I'll just very quickly review something that everybody knows about, barrier penetration in the WKB approximation. And since, of course, I should put the J on here for Jeffreys, but I have to admit that in the US, we uniformly call it the WKB approximation. And Jeffrey, this has unfortunately been dropped. In all American quantum mechanics books, we'll call this the WKB approximation. Of course, it's this very familiar form for the probability given as an integral. It's useful here maybe an aside to point out that you can actually rewrite this formula in a rather suggestive way, because there has to be, by the mean value theorem, there has to be a value of the coordinates z somewhere between the two classical turning points, so that this thing's actually equal to the integrand evaluated at that point. And then if you consider a particle that had a speed given by essentially the energy equal to the difference between this value and the top of the potential, and then V is essentially twice the speed times the width of the barrier in units of the Compton wavelength. That's a rather simple way of seeing what the WKB approximation is saying. So of course, as you can kind of guess from this makes it more clear. The WKB probability has to decay exponentially as you increase the width of the barrier, keeping everything else constant. So what about large radiation pressure fluctuations, though? So what we're interested in is the possibility that a large radiation pressure fluctuation could temporarily give the particle enough energy that it could essentially hop over the barrier before it has to give the energy back. And in fact, this is somewhat analogous to a phenomenon that's well known in thermal physics of thermal activation. at finite temperatures, you have a small population of particles that already have energies above the barrier, so they can go over. So there's a competition between the quantum tunneling rate and the flying over of the high tail of the Boltzmann distribution. Well, I will not going to talk in detail about how we analyze this. I'll just point out that what you need to calculate is the cumulative probability distribution to have a fluctuation that is larger than a certain value. And the x here is going to be a certain value of your sample stress tensor, which happens to be the value which we show in our paper is we calculate a formula for it, which is the value that would be able to push the particle over the barrier. So it's going to have some form like this. F of x, where f has this form. So the crucial thing is that the integral of a function of an exponential like this is still going to have the same exponential in it. So basically, if f is smaller than g, then the probability of jumping over the barrier due to radiation pressure fluctuation will be greater than the probability of quantum tunneling. And we show that in fact there are cases where that does happen. You have to do that. It's not something you would see very easily. It doesn't happen at low energies. So most of the experiments on quantum tunneling that are done at low energies, the radiation pressure effect is probably negligible. But the other thing here is there has to be something that determines what the sampling function is, and particularly what's the critical value of alpha that comes into that sampling function. And our view is that it should be determined by the details of the physical system. And in this case, although this is something that needs more work, we propose that it's perhaps a combination of the shape of the barrier, the potential, and of the particle wave packet. So if those both are strictly zero outside of a finite range, then nothing happens until the leading edge of the wave packet touches the barrier. That is some kind of a switch on. But this is still a little bit vague. But we did do some calculations and found and argued that you might be able to explain certain physical, rather mysterious physical effects, which, of course, this is a conference on gravity. Now I'm talking about very nitty-gritty nuclear physics. But it was when people first created heavy ion accelerators and start slamming small nuclei into big nuclei, like oxygen-16 into samarium-144, the nuclear physicists were amazed that the fusion cross-sections were much higher than they had expected. And they're much higher than are given by the simple quantum tunneling models. Now, there are nuclear physics explanations for this, as coupling, deformation of the target nucleus and coupling of multiple degrees of freedom. But we suggest that in fact maybe quantum radiation pressure fluctuation could also be a viable explanation, at least, or it's consistent with order of magnitude estimates that they could give enough effect to explain this. Okay, well, let me spend the last few minutes talking about a few other effects of large energy density fluctuations. One might be black hole nucleation. That is, if you have large energy fluctuations in flat space-time, you might temporarily create a small black hole. But it wouldn't last very long because it would be surrounded by negative energy and probably be evaporated before it has a chance to emit any Hawking radiation. But just for fun, using the Lorentzian result, we calculated some black hole nucleation rates and said that if you wanted a black hole of 1,000 Planck masses, then you'd probably only get one per horizon volume per age of the universe. So that's not very interesting. But if you're willing to settle for only 400 Planck mass black holes, the rate goes up dramatically, and there should be about 1 cubic centimeter per second. Now, of course, they presumably only lasts a few a few hundred Planck times at the most, so you don't notice them. But that's at least the potential possibility of very small black holes being nucleated by these fluctuations. An even more exotic application might be the Boltzmann brain nucleation. I should say that Boltzmann brains are of interest to people who want to do anthropic reasoning and count observers, because if you're trying to use anthropic arguments to limit our universe, you have to know how many observers there are. And the question is, if observers are not necessarily restricted to be in galaxies, but are things that could nucleate out of the vacuum for a little while, or at least out of the Davies vacuum of de Sitter space, that would complicate anthropic reasoning. I see. Somehow, in creating this, somehow Page's estimate got lost. But our estimate was of the rate is e to the minus 10 to the 26. And it really doesn't matter what units you use. You can use almost any, you could use SI units, or you could use Planck units. It doesn't really, it's the same number. That doesn't seem like a very impressive rate. But Don Page had also done a much earlier calculation, assuming an exponential probability distribution, and he got e to the minus 10 to the 50. So that's an enormously smaller number. So this vastly increases the probability of Boltzmann brains and might complicate anthropic reasoning in some way. Okay, this kind of illustrates the picture that ordinary biological observers like us have to be around certain kind of stars of the spiral arms of galaxies, but Boltzmann brains have a vastly larger volume in which they can nucleate, so they might outweigh us. Okay. Another thing is that Carlip and co-workers used a version of the large fluctuations to argue that large positive fluctuations on small scales will tend to lead to something they call asymptotic silence, where the space-time breaks into small causally disconnected regions. So that's another possibility. And then I'll just mention other things that are not yet really been explored too much are non-Gaussian contributions to primordial density or gravity wave fluctuations, or other large passive fluctuations of the gravitational field driven by quantum stress tensor fluctuations. But since my time is running out, I'll stop and summarize. So of course, the first part of the talk I told you about how the work at King's in the 70s was crucial for the development of quantum field theory in curved space-time. This included things like the conformal anomaly, calculations of the stress of the expectation value of the stress tensor, and back reaction Hawking radiation, and also other studies of quantum inequality effects and the notion of quantum inequality limits that were first done here at King's. And then this really gave the basis to some more recent work on probability distributions, whose lower bound is the quantum inequality limit, and the to me exciting idea that there could be very large positive fluctuations of the stress tensor that may have interesting physical consequences that need to be explored further. So I think at that point I'll stop.
Thank you. Do we have a question?
I was intrigued by that fraction 23 over 24. Polyakov showed that the critical dimension of the bosonic string, which is 26, follows from the conformal anomaly of a two-dimensional scalar field. And I was wondering whether your 24 is related to Polyakov's 26.
Well, indirectly, because actually in our paper we give a formula in terms of the central charge. We do this for general conformal field theory. And I think it is something, the exponent for a general central charge is something like 1 minus c over 24. So of course, the example I gave, the massless scalar field, has a central charge of 1. So that's how you get 1 minus 1 over 24, which is 23 over 24. So there is a connection through the central charge.
So if you use the fluctuating stress tensor in the gravitational equation for the probability distribution, and you given that one of the ones that you calculated, would you get interesting effects for a geodesics traveling along the universe for a very long time?
Well, that's
appreciable.
Yeah, well, that's something, in fact, we're thinking about. Part of the issue is what is the averaging? What is the sampling function you have to use to describe the stress tensor fluctuations? And it might be possibly described by the wave packet or the world cube of your particles. But of course, is that if it has a very long time, then the sampling time is very long, which will tend to suppress the fluctuations. But if you have any finite travel time, then of course there is a possibility of getting probably a larger probability of getting a fluctuation over a shorter time than there is over a very long time. But that's something I think is not yet worked out so clearly. I mean, I did do some work earlier with former student Jacob Borgman, where we looked at the variance of the expansion fluctuations using the Ricciardo equations, the Langevin equation. But this was before the work on the probability distribution. So we were just looking at the mean squared fluctuations, not at the probability of large fluctuations.
Maybe another question, if you repeat this, can you calculate this probability distribution also for, let's say, a state describing the scattering of particles, let's say, very, very high energy? So people talk about this TV gravity. So assume that maybe the Planck scale is a bit lower and you have a state like at the LHC particles.
Okay.
You have two particles.
Well, so far these are results for free field theory.
You could have a superposition. You could do the calculation of free field theory with the state, with the outgoing particle.
Yeah, that's possible. Also, these were results for vacuum states.
Yeah.
But you could
So
certainly I think it's
that's
certainly
a-
possible to generalize this to much more general states like you're talking about. So that's an interesting question. And let's say the short answer hasn't been gotten yet.
Okay, let's thank Larry again.
Well, it's a great pleasure for me to be back at King's after all these years. I think perhaps I'm the person who was here earliest of all people in the audience. 1961. Any hands? Yes, something else. 1961, 62, and then 62, 63. Anyway, it's a pleasure for me to be able to talk about conformal things. I hadn't quite realized it was meant to be just a historical talk, which it won't be. It'll be partly a historical talk. So let's start with the historical stuff. I shall probably have to move something or change the focus. Can I make the picture smaller?
Let's see. Focus. Off. Here we go. Like this?
Probably do. Thanks. Yes. Focus, is that? Or has it focused itself? I think it does itself.
Cool.
It's all right as far as I can see, but then my eyes aren't very good.
Better?
Okay, thanks very much. Well, this was a question of well, black holes spiraling into each other and radiation coming out. And the issue that we heard about, the discussion about earlier, about, excuse me, about energy that would be emitted by this. So the question of energy loss. And there was work by various people, which I'll come to. First of all, there's a question of what you mean by energy in general relativity. And this is a problem because energy is not local. And I think that it was always a difficulty for people in the old days when they first heard about general relativity, even to take it seriously, partly because you didn't have a local energy density. And there are all sorts of ways of talking about this. And this was, if you had a local energy density, there wouldn't be a problem. But anyway, could you define energy in some way? And this, one of the earliest ways of doing it was to think of an integral to infinity, and that would be the, say, the Arnold-Misner method. Now I have here a space-like section to this situation here, and you imagine that out at infinity you have some integral which tells you what the energy of the system is, such as the Arnold-Misner energy. And the trouble with this, of course, is that if you let time evolve, then the energy intersects the waves, and it keeps on doing so, and so that any energy which is carried out by the waves will not be, you can't get an energy loss expression in this way. So this is one of the troubles, and to understand how to do this, it's best if you can consider some sort of coordinate system, which is null. So if this is one of your coordinate surfaces, and you have an energy defined out at null infinity, then as you intersect some of these wave regions, then you might expect the total mass energy to get reduced. And you could tell the energy loss, that such as an energy calculated from here, the energy calculated from here minus the energy calculated from there would give you some energy flux that was described that way. So this was the work that Bondi did. Well, I said Troutman originally had an expression for energy flux, but I think Bondi was the one first who had an expression for the total energy of the system and related that to the energy flux. So perhaps we can distinguish those two contributions. The Troutman one was a lot earlier, but the Bondi one was more comprehensive and enabled us to have measure at any one retarded time what the total energy was. Anyway, I heard a lecture given by Troutman, I think it was when I was in Syracuse, that was in 1961, rather than at King's, in which he was explaining his study of the asymptotics, and in particular the fact that the gravitational field had the null form for its leading term, and all these things. And I remember being very impressed by his talk, but it was very complicated, full of all sorts of calculations. And I don't like thinking that way. I prefer to have a geometrical picture of what's going on, and I found that a little worrying. So I tried to think, well, is there any way of looking at this in a more geometrical way? And at that time, at Syracuse, there were various people of great distinction in general relativity. There was Peter Bergman, who had been Einstein's last student, and he had a group there that encompassed many people. Arthur Kolmar, I remember. Ted Newman was there when I was there, and I got to know him well. I'd known him a bit before that. Andre Troutman was there part of the time, and Engelbert Schucking. I shared an office with Engelbert Schucking, and he stressed to me the fact that Maxwell's theory was conformally invariant, which I hadn't known before. And if you want to talk about radiation in Maxwell's theory, you could make advantage perhaps of its conformal invariance. Well, I was very familiar with conformal transformations when applied to positive definite. Well, I was thinking of Euclidean space and how you can convert it to a sphere, and you have stereographic projection and all this sort of thing, and how circles are preserved. So that kind of geometry was familiar to me. So I began to think about applying the idea, could you look at infinity in the case of Minkowski space, say. Well, that's fine. Could you look at infinity in the case of the short-shot solution? And I was thinking of going out in space-like directions, and so that wasn't much good because the short-shot short-shot solution has a singularity at infinity, space-like infinity. So I thought, well, this idea doesn't work. So I went away, and it was when I came to London after that, in the autumn of 1961, I began thinking again, because I had been impressed by Ray Sachs's work, which generalized what Bondi had done, and also his work on the asymptotic behavior of the curvature tensor along light rays, and the fact that you get this peeling property in the principal null directions. The leading term is term way out there is you have all the four principal null directions pointing all at once, and then you get one off, and then two off, and then three off as you come in. And so that was a very remarkable geometrical property. And I began thinking again whether this could be understood in terms of properties of infinity, but it was clear that you're going out to null infinity. And it was only then that I realized when you go null infinity, you have a 1 over r rather than a 1 over r squared. The behavior goes bad only it's 1 over r, not 1 over r squared. And so there was a chance that things would be finite. And so I looked at Minkowski space and things like that, and realized that in fact it was quite reasonable to expect that you had a finite behavior at infinity. So this was really when I started thinking about, well, first of all, Minkowski space, and then looking at more general situations, such as the Robinson-Troutman solution, and that clearly had a non-singular, what we now call scry. I should explain the term scry. That means conformal infinity. Often people think it means something that I was very knowledgeable about, such as Polish, when it means boundary. And I think people have pointed out the word descry, and I think there's another word which has something to do with crystal balls. I've forgotten what it is. But none of that had anything to do with it. It was just a boring thing that I think Ray Sachs had complained that I'd used a script letter for this, a script I, and he said that's a terribly bad notation, that nobody would ever use that letter. And how would you say it, you see? So I thought we've got to have a way of saying it at least. It just means script I, which is really pretty unsophisticated. Nevertheless, that's what scry means, script I, and it means infinity. I stands for infinity. So nothing very interesting. Anyway, so this is just saying that you have problems with not having a conservation law in the sense of having a strict, something like a conserved, well, you have the tensor, of course, has got too many indices, only two. In fact, it has a conservation law of a sort. It's only a conservation law in flat space or under certain other circumstances, but it's not generally a global conservation law, so you need to do something else, and these are various things. Let me not go into that, but if you have a null infinity, then perhaps you can look at what happens on the boundary. So that was the way I was looking at things. And it turned out to be a nice way of looking at things. This is the pictures inspired by Minkowski space, where you have a conformal boundary. In the case you have a future null cone, roughly speaking, it has a vertex at the top and another vertex at the bottom. This looks like a single point, and it's a bit harder to appreciate that that's just one point. And you've got one point at the bottom, so you have these nice smooth cones, infinity. Now, of course, the question of whether this makes sense in more general circumstances, it has a lot of questions that people say. There was a question earlier in the talks about whether it makes sense in general, in null infinity. It depends what you mean by in general. Let me just give you my point of view on this. See, my point of view was that if you're looking at Maxwell field, well, Maxwell field is conformally invariant, as Engelbert had explained to me. And therefore, you can Maxwell field doesn't really recognize infinity at all. It's just as though that's just somewhere, any old place. It could be infinity is just like anywhere else, so it just goes sailing through it. And so you would register what the value of the field was on the boundary, and that gives you the radiation field. So that's a very nice way of talking about Maxwell field. What about the gravitational field? Well, here's the thing which I always found very curious when I started thinking, well, really thinking about spinors and so on, but let's not worry about that here, is the conformal behavior of what I regard as the degrees of freedom in the gravitational field. I take it to be the Weyl tensor, the Weyl conformal tensor. Whereas in Maxwell theory, you have the Maxwell field tensor, the F, and you've got the J, which is the source. And so the two tensors of importance, they're different differential order. Whereas in the case of gravity, you've got the thing corresponding to the source, which is the Ricci tensor, trace reverse Ricci tensor, and the thing corresponding to the field is the Weyl curvature tensor, but they're the same order of differential order. Well, that has to do with the spin being 2 instead of 1. So nothing wrong with that. It's just that the two parts of the curvature tensor, namely the Weyl curvature on the one hand represents the free field, and the other part, the Ricci tensor, or its trace reverse part, which represents the source of the field. Now the Weyl curvature is a conformal curvature, so it's clearly a conformally invariant thing. But if you're looking at the propagation equations, which in the case of general relativity is the Bianchi identities, well, it's easy to see in spinor form, but I won't worry you about that. But you have zero Rath mass fields, and you have an equation in flat space with any number of indices you like, and that corresponds to the different spins. And these massless fields are all conformally invariant with the same conformal factor. And so you can understand them as a whole. Well, this thing K is basically what you get for the spin 2 case, and this is a conformally invariant equation too. That is to say, in vacuum, the equation of propagation of this thing is a conformally invariant equation. However, it has a different conformal factor. And I always found this very strange. It has a key role to play in what I want to say later, but let's come to that later. The point here is that if you have, say, and when I'm putting a twiddle on it, that means the physical object. I think I haven't quite consistent because I here had a circumflex, but never mind. That's meant to be the physical quantity, that is to say, in the physical metric. And in the case of Maxwell field, with the indices down, these two are the same. In the case of gravitation, I'm going to make K equal to C. So K is describing the gravitational degrees of freedom. But when I do a conformal transformation, I want this, let us say, conformal rescaling by making the G's scale with this thing I'm calling omega, then this, the C's and K's scale in a different way. So this means that if you have a gravitational field, again, doesn't know where scry is, if you like, it just goes sailing through. Think of how it's propagating according to the Bianchi identities. That's the analog of the Maxwell's equations, if you like. And that field, say if it was in flat space, it wouldn't be interested in scry. It would just, scry would just be like anywhere else. And so it would have finite values here. However, because of this relationship between the C and the K, the Weyl curvature, let's say the conformal curvature, actually goes to 0 at the boundary, which is rather nice because it means that the structure of scry is more like the structure of Minkowski space than you might have expected, because there is gravitational field making its mark up there, but it's only in the derivative of the normal derivative, if you like, of the Weyl curvature that you register something. The Weyl curvature itself is 0 in scry. Anyway, it does make the discussion of infinity easier. So I was taking the view then that the gravitational field, again, sort of goes sailing through without noticing it. And so if you had Minkowski space, there wouldn't be any problem, and then you have a bit of gravitational field, that wouldn't cause any problems with it either. The problems come from I+. So if you have a gravitational field with a mass, then that produces a singularity. Sorry, I0, I meant to say. The problems come here. You have a singularity there, and that singularity might propagate its singularity up the cone in some way. So, in fact, if you're looking at fields which are retarded so that the radiation is going out, then the radiation going out isn't going to cause any problem in addition to what comes from my zero. Whereas if you're looking at something where these sources, I mean, they look as though they're coming from close together, but they could be coming in from infinity and then spiraling around each other. And as they come in from infinity and spiraling around, there would be a little faint radiation coming out at the back there. And this radiation, although it looks faint, when you squash it down to this picture, it will concentrate itself on the boundary. And so you might expect that there would not be a very smooth square minus in situations like this, but you could expect a smooth square plus. And in fact, there is a difficulty, as Helmut Friedrich certainly has made clear, if you want to try and make the thing smooth both ways at once. My own view is that you make it smooth in the future, and you don't necessarily expect the past to have a very smooth scribe. It could be there. It's useful to have it there, even if it's not that smooth, because you want to say you're looking at retarded solutions, perhaps, and you don't care much apart from the fact that you've tried to kill off what's coming in the form of radiation, and that's rather crude. Whereas the structure of the radiation going out, you could study the detailed properties of it using the smoothness out there. So I think the issue about whether scry plus is smooth in general cases, my expectation is that it is, provided you're not asking for it to be smooth in the past as well. To make it smooth in both ways at once, with some high degree of smoothness, is probably much too tall an order. Anyway, let me leave that here. I think there's still questions about that issue. What I want to come to next is the relation to the cosmological constant. I seem to remember, this is something I did on an airplane. People sometimes ask me whether I have a good idea in a dream. I've certainly thought I've had good ideas in dreams, but when I wake up, they're always rubbish. This came up in the discussion with Yahya Aharonov, because he said several of his ideas had come in dreams, and I envied him on that, because my dreams are no use at all. But I'm just trying to think why I was saying that. Yes, it's not dreams, it's aeroplanes, that's what it was, yes. So this was an idea I had on an aeroplane, which also isn't a very promising thing for having ideas. But I remember talking to Wolfgang Rindler, and I should say Wolfgang Rindler was one of the people that I think I met him first at King's College, and in fact I shared a room with him in 1961, 62, and that was where we talked about writing a book on spinors. It took a long time since then until it came out, but this was where it actually originated. But I remember Peter Sekaresh was around as well. I can't remember too many of the people, apart from ones who've been mentioned already. But Wolfgang was certainly somebody who influenced me, and he had this notion of how you understand horizons in cosmology. I think the whole subject has been very confused before his contribution, because there are different kinds of horizons, and he made it clear that the difference between the particle horizons and the event horizons and so on. But then I thought to myself, I had this time on the plane. This was going to a conference that Tommy Gold had organized in Cornell. And in fact, in those days, they had, I can't remember, but he had money enough to treat everybody to first-class flights on the train. And this is my first time I'd ever been, not quite the first time I'd ever been on an airplane, it's the first time I'd ever been on a long trip on an airplane, certainly. And I was a bit nervous. But since I was first class, they gave free drinks, and that means I could sit there and not worry about the engines wobbling like that, which is, of course, what they always do, and get used to that after a while. But I decided I was going to think about these horizons, and could we understand it in terms of conformal infinity? And it worked out very beautifully, just as sort of as I was expecting, although I hadn't quite seen what these horizons were before looking at Wolfgang's paper. And it's just a question of the cosmological constant. So if you have a cosmological constant, and let's say massless fields, so they don't go and muck up scribe too much, then if it's just simply if you have a positive cosmological constant, then you have a space like scribe plus, and then you can see that the different world, these are meant to be different world lines hitting scribe plus, and their pass cones represent the ultimate information that they can receive. So pass cone of the intersection with scribe plus, if you like, of these world lines, and those are therefore the horizons, and the horizons are very easily understood in terms of this picture. You just take the pass cones of the points of intersection of future world lines. What about the, now this is a scry in the sense that this is a null infinity. In the case of the particle horizons, it's a question of the Big Bang. And the Big Bang, at least in normal situations, certainly in the Friedman, Lemaitre, Roberts, and Walker models, the Big Bang is space-like, and that's how you understand the particle horizons. Well, if you have a world line here, say, and this is us looking back, then the pass-like cone will intersect only a certain part of the Big Bang, and then you can look at all the particles which come out from there, if you like, and you'll never have any, or at least never is the wrong word. If you waited long enough, you would, your pass cone would increase in its scope. There would be an ultimate horizon when it becomes your event horizon, and then the total region that can ultimately be seen will be where the particle, well, the galaxy world lines meeting the particle, meeting, I don't quite know how to say this, the ultimate particle, the ultimate event horizon will encompass all the particles that you will ever see. And so those within the particle horizon, that's the ultimate particle horizon. Anyway, it seemed to me that these pictures make these ideas of horizon much easier to understand. And I've always thought about it this way. And some of these other pictures where people have a Big Bang all squashed down into a point doesn't seem to make too much sense to me. But it does indicate that the space-like nature of the Big Bang is very curious, and it means that things here seem to be independent of each other. And I used to worry about charged particles, for instance. Could you have a charged particle created at the Big Bang? Well, you see, it would have to have its electromagnetic field created. If you couldn't have a charged particle here without having a negative, just a positive charged particle by itself. It would have to be accompanied by lots of other things also on the Big Bang at once. So you have conditions which relate, constraints, if you like, which wouldn't necessarily be generally happening. Anyway, these issues troubled me for quite a long time. I can't see what I was saying at the bottom. Yeah, yes, this is the point about strong cosmic censorship. To say it's space-like, you see, you might have more complicated initial states. There could be something very complicated. And I used to worry about that too. It seems to me, why do we take the Big Bang to be very like a Friedman, Robertson, Walker, Lemaitre model? Why don't we consider much more general singularities? And of course, then Stephen Hawking and I produced these singularity theorems which show that you've still got singularities in general expanding cases, even if this was very irregular. I remember talking to Jim Peebles at one point and complaining, why don't people consider these much more complicated situations? And he made the comment, well, it's not like that. In other words, the evidence from the cosmic microwave background is telling you that it's not complicated, it's all very uniform. This had a big effect on me because I hadn't quite realized that, in a certain sense, the singularity theorems don't tell you much in the past because the singularity structures are very much like the conventional cosmologies. In the future, they're very different because you've got to collapse to a black hole and you have a great mess. And so to know that that is actually a singularity in general case is really something, telling you something important. Whereas in the case of the Big Bang, these other possibilities just aren't there. And why aren't they there? And that's a thing which is been of interest to me for a long time, and I'll come to that question in a minute. Well, the issue of what kind of physics is appropriate to conformal geometry. Here I have a picture going the other way here. So this is a picture which is just showing the light cones, and if you have massless physics, basically, general relativity is a bit different. But if you have Maxwell fields or anything else which massless fields, apart from GR, which actually affects the structure of the space-time, or if you like, weak field GR, which is just considered as a linearized theory or something, then you've got the light cone structure. And Maxwell fields don't care about the metric structure. So you have this picture, if you want what's interesting to massless fields, and this picture here where you put the scalings in. So those are meant to be the scalings giving you the see, the light cone is basically 9 components per point because it's the ratios of the 10 components per point. And the remaining component, which gives you the scaling, that's just one more. So that the light cone structure is almost all the structure of the space-time. It's just a little bit more, if you like, a scalar sort of field, which determines the structure that you need for space-time full general relativity. Now, full general relativity is now confirmed to very great precision. In fact, when you drive your car and you use the GPS, of course, that's because the clocks are so good, and they have to take into account the space-time structure according to general relativity, and you get the wrong answer. You'd be way off. So we have marvelous clocks. Now, marvelous clocks, seems to me, come about basically because of the two most fundamental formulae of 20th century physics. One of them, of course, has to be Einstein's E equals mc squared, and the other is Planck's E equals h nu, where nu is the frequency. And if you put the two together, of course, you get that the frequency and mass are equivalent. In other words, if you have a particle, which is a stable particle, that particle is a clock, just naturally by these two fundamental laws. That has a natural frequency, which is absolutely comes down to these two very fundamental physical principles. And that is ultimately why we have such incredibly precise clocks. If you want to measure distances, it's no good going to Paris and looking at the meter rule. You use the light second, if you like, and then you define your meter in terms of a light second, which is very much more precise, because these clocks are all around. But the flip side to that is that if you don't have mass, you don't have clocks. So that it's why, in a certain sense, that if you don't have any mass, then the light cones are good enough. But if you do have mass, and when I say that, then that will now include general relativity, because mass is, of course, mass energy is the source of gravity, and so the mass is the source of general relativity. So the general relativity needs to know what the scale is, but if you just didn't have anything to do with mass, then you wouldn't need to know the scale. So that's the sort of picture I like to have. Okay. Now I've been telling you things which are fairly straightforward, I hope. I now want to say something about the universe. So here's the picture of the universe. Well, you might question certain things about this picture. And one thing is, what's all the frilly stuff at the back? Well, that's only there because I don't want to prejudice the issue as to whether the space-time is open or closed. See, it might be closed up, or it might keep on going. But I'd like to use the same picture, whether or not it's open or closed. So that's the only reason I put that stuff at the back. I don't care what's happening. Well, I care, but what I want to say, I don't care. Time, of course, got rather rubbed off, but time is going up the picture. There's the Big Bang, and here we have the expansion according to Einstein's equations, and here we have the lambda term starting to positive cosmological constant, or dark energy, or whatever you like to call it. I prefer to call it the cosmological constant. It does seem to be consistent with just simply being a cosmological constant, and so as far as observations are concerned at the moment, that's fine. Of course, you might question whether I shouldn't have put in this picture inflation. There's one good reason why I haven't, and that is because maybe I have. That is to say, inflation will be tucked into that little black spot, and you wouldn't know it on this scale. So you need, of course, to have a magnifying glass to see it. And then you get a picture which is something like this being the handle of the magnifying glass, of course. And here we have something which is allegedly, at least, very much like the exponential expansion that we do seem to be indulging in, and which is consistent with the positive value for the cosmological constant. There's a second reason why I haven't put inflation in this picture, and that is I don't really believe it. Now, this is where I get into trouble, of course, because everything I've said up to this point is pretty conventional physics and cosmology, but inflation has also become conventional. When I first heard of the idea, I wasn't at all happy with it, and I thought I would give it 2 weeks and then it would disappear. Of course, that was completely wrong. It's a dominant part of current cosmology. I had the feeling, I still have the feeling, that a lot of the initial reasons were incorrect. One of the reasons for putting inflation in was that you had such smooth universe, as I mentioned before. You have a very closely Lemaitre Robinson Walker model. And the argument was that it was irregular to begin with, and inflation would stretch it out and make it all nice and snap. Almost flat and almost, well, the flat is not what I want to talk about here. Almost smooth. Now, that argument I never believed. I'll come to that in a minute. There are, I should say, good and bad reasons for inflation. There are certainly good reasons for it, and if you don't believe in inflation, as I claim not to, then you have to have explanations for the reasons which it is good for. And I'll come to those in a moment. But let me, first of all, come to the things where I claim it's not good for. The main one being, well, the equalizing of temperature, also I don't think it's good for either. But let me mention the point where I think why I claim it doesn't smooth out the initial singularity to something very uniform. This comes to the very fundamental law that we've been hearing about before in the last talk, the second law of thermodynamics. Second law of thermodynamics, well, this is the thing that I like to call the mammoth in the room. The second law of thermodynamics, more or less, tells you that things get more and more random as time goes on. Well, the entropy is really increasing. Okay, entropy is increasing. That's fine. Not decreasing, or if you like, but it's increasing. Another way of saying exactly the same thing, go back into the past, and the entropy is decreasing. So that means it goes back down and down and down and down and down until you get close to the Big Bang. Well, what do we see of the Big Bang? What's one of the most important reasons for believing in the Big Bang? Well, it's the cosmic microwave background. In the cosmic microwave background, what's one of the most striking features of it? Not a puzzle, because people are rather expecting this. But nevertheless, a puzzle from the point of view of the second law, because what we see apparently is this Planck spectrum. This is the picture produced by the original, what was it again? Sorry, the name's got in my head. And the original measurements of this thing. Oh, forget it. Anyway, these are the error bars. This is the Planck curve, and the observations. These are error bars on the observations. And you will see that they are exaggerated by a factor of 500, so even the worst ones down here are still within the thickness of the incline. So we have a very precise agreement with the Planck curve. And what does that tell us? That tells us when you get back to very early stages of the universe, you've got thermal equilibrium. True, you've got expansion, but that's essentially adiabatic, as was properly understood a long time ago. So it's nothing to do with the expansion. The expansion, it's still thermal equilibrium apart from expansion, and that doesn't change the fact of the Planck curve. So you have a very high entropy situation. That's the mammoth in the room. You go back and back and back in time, you're supposed to find a low entropy situation, and you seem to find a high entropy situation. Well, of course, as I've said many times, this is not a paradox. It's just that you've taken into account in this thing only matter and radiation at the same time. And matter and radiation in equilibrium, apart from expansion, that's fine. And it's also consistent with the very uniform nature of the sky. And this is sort of thing you get with the gas in a box. If you tuck it up into one corner and then let it spread out, that's entropy increasing in terms of uniform distribution. And the Planck spectrum, if you had matter and radiation, that's fine. So that is high entropy. However, if you were thinking of gravitating bodies, and this could be a huge galactic scale box with a lot of stars going around, they will start to clump. And so what you see is a mixture of this and this. So you see very high entropy with regard to the matter and radiation, very low entropy with regard to gravitation. And this is just a huge imbalance. Now, although there are all sorts of models and cosmological schemes and goodness and this and that, nothing, as far as I can see, apart from what I want to tell you shortly, seems to explain or give any reason for this huge imbalance. Lee Smolin has a nice way of putting it, that you have two completely different temperatures. You've got this very high temperature here and very low temperature with regard to gravity. Gravity was sort of aloof in the Big Bang. It didn't take part until very slowly in all the physics that's going on. So you have a Big Bang which was extraordinarily random in one respect, extraordinarily unrandom in another respect, just those two respects being just two different physical forces, if you like. Or let's say two, gravity and all the rest. So that's the issue. What's the reason for that? Or, well, of course it's very fortunate, because I don't want to go into this here, but the sun is there. We don't get energy from the sun because the energy from the sun all goes back again into the sky, but we get low entropy, the energy in a low entropy form, and it goes back in a high entropy form. And that's due to the temperature imbalance between the sun and the dark sky. And that comes about through the gravitational clumping which produced the sun. So all that stuff is very important to us. Now, why don't I think the... well, suppose we had a collapsing universe. This is my same picture, but turned upside down. And there would be, say, black holes forming in this collapse. And these black holes congeal and make an incredible mess. And this would be, if it's this model, but with certain irregularities. So imagine that we perturb this a little bit, and these black holes congeal and make one great mess at the end. Okay, so that's the picture. Now, this is a much more general singularity, where indeed the gravitational degrees of freedom would be excited and everything would be extremely high entropy. Gravity entropy would be up now to an enormous value. Now, of course, you could, if you like, put the inflaton field in here if you like. It doesn't make any difference to this picture. You would still get entropy increasing, inflaton field or not. Of course, we don't know in detail what this looks like. It might well be some kind of a BKL, Belinsky, Galatnikov, Lifshitz, and Misner, I should put in there too. These people who discussed these very complicated kinds of behavior that you could get, whether Bianchi 9. Now that is a high entropy singularity, and this you can estimate how unlikely that is as compared with that by simply looking at the Bekenstein-Hawking formula and making some estimate as to what the possible degrees of freedom there were because of all these possibilities here. You just look at that formula and you come to the conclusion that the chance of this, if it was chosen by random as opposed to that, is something like 1 part in 10 to the power 124. Well, 123 I used to say, which I got from Don Page, but 124 because I didn't include the dark matter in those days. So it doesn't make any difference. Just like the number that you gave us, that was a slightly smaller number. But you can replace 10 by E and E by 10. That's the problem. It doesn't make any difference either. So all the units there certainly don't make any difference. But that is much more likely. So you might say, why did the universe start off with that and not that? And the inflaton field does nothing for you. Because the inflaton field would have to, if it started that way, you would have to reduce the entropy to get to this. And it just means... anyway, I'm sure, I know a lot of people who work with inflation understand that, and it leads to the Boltzmann brain problem that you talk about too, and all these things. But it seems to me that inflation doesn't do that. That was not a good reason for inflation, because it doesn't smooth out things like this. Another point I was making is that you might question whether this could be regarded as an instantaneous event, but if you have cosmic censorship, then that should be space-like. And if that's space-like, then you can consider it as an instantaneous event. So I don't quite see why not. Of course, it might be cosmic censorship. Strong cosmic censorship is wrong. If strong cosmic censorship is wrong, well, still it doesn't help you much, because there will be a whole lot of solutions which are consistent with strong cosmic censorship. And so why are they not part of the initial state? So I don't think any of that is an explanation for the smoothness. However, inflation does do things, which one of the most notable is that you have this fluctuation in the temperatures, which is scale invariant to a large degree. There's also the spectral parameter, which tells you it's not quite scale invariant. But nevertheless, that's a very striking feature. And how do you explain that? Well, you see, inflation has a go at explaining that, because, roughly speaking, you've got this type of self-similar space-time, and that's a self-similar space-time if you've got some quantum fluctuations going on in it, that might give you that. I have difficulties with that too, how quantum fluctuations can actually produce a macroscopic classical things, but I'll come back to the view that I have on this in a moment. Let me get back to the conformal issues. This is basically reiterating what I've been saying about infinity. Apparently we have a positive cosmological constant, and so that apparently we can squash infinity down conformally to make a space-like future boundary. The Big Bang seems to be very smooth. Well, let me say what I'm saying here. Because of the cosmological constant being positive, we also can appeal to Helmut Friedrich's very nice results here, which tell you more or less that if you have massless things in the remote future, and it's a very reasonable situation to assume that, very generic in certain respects, that this should be give you a nice, smooth, conformal boundary. So it's really a nice thing as far as the conformal infinity is concerned that we do have a cosmological constant, because that means we can use these conformal ideas, and that, as Helmut has shown us. What about the Big Bang? Well, the situation is completely the other way around now. To have this being a smooth conformal boundary is an enormous constraint. So, I said yes, it's very, very special, but it's very, very special, seemingly in a way that we like. In fact, what is the way in which the universe was special? Well, I used to say things like the Weyl curvature hypothesis and things like that. which is to say that the Weyl curvature as a hypothesis, not as an explanation of anything, but just to say that singularities of past type should have vanishing Weyl curvature. Now, I used to worry about this because people tend to take the view that the Big Bang, whatever it is a quantum gravity thing. Now, if it's a quantum gravity thing, that is to say, to explain it, we need quantum gravity, why is it that that doesn't work the same way for collapse? The singularities of collapse are very complicated. You expect to have enormously large Weyl curvature diverging to infinity, and quantum gravity is supposed to come in there too. However, it has nothing, doesn't smooth out the singularities as far as we can tell. I don't think, only if it did it at the last minute, I wouldn't really notice anything really. So it seems to me for a long time that if it's quantum gravity must be a very lopsided theory. It must be a hugely time asymmetric theory because it does something completely different to the Big Bang from what it does to the singularities in black holes. And so this has been a kind of problem I've had for years, worrying about how quantum gravity could be completely unlike all other quantum field theories, this utterly time asymmetric theory. Well, the view I'm going to describe here is that it's not quantum gravity. Now, this is a somewhat outrageous view, especially to many of my friends, that the Big Bang is not actually a quantum gravity thing. Well, how do we talk about it? First of all, how do we say that rather than saying the Weyl curvature by hypothesis is 0 at the Big Bang, that's sort of awkward, even because you can't even quite say what it means without saying a lot more. I mean, to say the Weyl curvature which is singularity, there isn't a notion of a tensor like the Weyl tensor when it's at a singularity. So you've got to say something like the limit in some way. And talking about limits is awkward. The same sort of reason I didn't like talking about limits when going out to scry. But Paul Todd has a much better way of talking about this. So Paul Todd's proposal, let's take this away now, is that the Big Bang was something that was conformally extendable. And this is a really nice way of talking about the Big Bang. It doesn't quite say, as it stands, that the Weyl curvature is 0. It says that the Weyl curvature, however, is bounded. It's got to be nice and regular and smooth at the boundary. So it's like an ordinary boundary to a conformal manifold. But as we'll see in a minute, it says more than that in what I want to tell you. But it certainly is a huge restriction on the Weyl curvature at the beginning, and a very good thing to say as a possible hypothesis. Still a hypothesis, and it's not saying, it's just mathematical. As with scry, you see, when I talked about null infinity, I didn't claim there was anything on the other side. It's just a nice mathematical way of talking about the gravitational radiation. You get gravitational radiation going out, and you squash infinity down, and then you can talk about the various quantities that you might be wanting for energy or angular momentum or so on, by looking at the finite values that will be attained at a smooth scry. And that's just a mathematical trick. So that's one mathematical trick. And here's another mathematical trick. You just say the boundary, the Big Bang is to be something like this. Now, I'm going to say maybe that it's real. See, everything up to here is not outrageous. Now I'm going to say something outrageous. The outrageous thing is that on the other side, actually, the real world that we live in, there was something before the Big Bang. Now, is this sensible? You might say, well, what's the physics going on near the Big Bang? Well, here, of course, you have temperatures which are extraordinarily high. The closer you get to the Big Bang, the higher the temperatures. You get to higher temperatures which are higher than the Higgs mass, and so it seems that mass loses all meaning. Let's say the mass, the rest masses of particles because the energies will be far in excess of the rest masses of particles, and more so the closer you get to the Big Bang. So you might as well say you're doing conformal invariant physics, at least in the limit down here. So the particles, in a certain sense, if you track them back, why didn't they have something on the other side? So that's the view, I'm going to say. But what might there be on the other side? Well, here's where it gets outrageous. What I'm trying to say on the other side is that it was the remote future of a previous eon, as I'm calling it. And that, of course, is a bit wild. I should say that the remote future, of course, there's lots of things. The universe gets very boring when there's nothing much around except black holes. It gets really boring when the black holes all evaporate away. And the biggest ones will take about a googol years, 10 to the 100 years or so, in order to disappear. But then when they've gone, by Hawking evaporation, it's going to be incredibly boring. And this was what led me to think maybe it's not so boring if you're a photon or something, because time doesn't really, massless things get right up to the sky, so why not? So that's the point of view. Of course, there will be a few other particles running around, and that's an issue which one might worry about, and which I do worry about, and I'll come back to that. But let me just put these things up here so it's rounded. Okay, I'm going to get more outrageous because it's not just that I'm saying these boundaries are real and there's something on the other side, but what I'm saying is that what is on the other side. And I hope I haven't lost my picture. No, I haven't. This is the picture. This is what I call conformal cyclic cosmology. The history of our universe was just one, or is to be, right up to infinity of our universe, to be one eon, as I call it, E-O-N, of an infinite, perhaps, certainly I would consider it to be most elegant, if there are an infinite number of them, but perhaps one could get away with just a few, an infinite succession of these eons. And the remote future, cosmological constant, fits smoothly onto the next one. Now this addresses the issue of things like the inflation being useful for certain things. I said it has its good reasons and its bad reasons. The bad reasons are smoothing out the initial singularity into something fairly uniform. The good reasons are, for example, the scale invariance that one has in the cosmic microwave background spectrum. Another, I think in a way almost more compelling, is the fact that you have correlations in the temperature variations over quite a wide angle. And these correlations, if you just have a space-like initial surface and something over here and something over here, how could the temperatures that these give rise to be correlated? When, without inflation, in the conventional models, these things would never have had any relationship to each other. However, if you have a pre-Big Bang theory, such as this one, then you certainly can have the correlations, because whatever is going on in the previous eon would give you correlations in the next one. So I think that certainly is accommodated by this model. The question of whether the scale invariance is accommodated, well, we'll mention something to do with that in a moment. But that's work in progress. At least you have a prospect for it, because the idea here, if you like, is the inflationary phase, that I've got here, is not tucked into here, it is actually before it in a certain sense. There was an inflationary phase, but it was the exponential expansion of the previous eon. So that's the picture one has here. What about second law of thermodynamics? Well, this whole thing was driven by the second law of thermodynamics. So I see there's a clock in front of me. What is the time? When did we... I don't know. Have I used up my time?
5 minutes.
Sorry?
5 minutes.
5 minutes. Okay, that's useful. Thank you very much. Of course, we've had models like this before. This is the oscillating model, the Friedman model with positive curvature with no cosmological constant. And then Tolman had the idea of having this not quite repeating by having a certain model that he produced with two molecules, I think it was. But the black holes are going to give a far more serious problem, because how is it that the entropy can be going up all the time when you have a cyclic model? Well, the idea here is to do with what's called the information paradox. Of course, this Hawking had one view and then he changed his mind and had another view. Let me not go into the history of all that. I think Hawking was more correct originally, that information is indeed lost in black holes, and it's hard to see from conformal diagrams why this should not be the case. Conformal diagram of a black hole is here, and you get stuff, singularity, which just seems to destroy it. And how does this information somehow creep out to the outside? I've always had a lot of trouble with that. It doesn't seem to make sense to me. However, this has to do with the issue of whether unitarity is likely to be preserved in gravitational situations. And I have other reasons for disbelieving that unitarity, in fact, whenever you make a measurement, unitarity is violated, at least in the standard way of looking at measurements. So, to me, unitarity is not a God that we have to necessarily respect under all circumstances, and with black hole evaporation, I don't think we have unitarity, and I think we do have information loss. And this is meant to be a sketch of phase space, and when black holes disappear, they carry away, well, if you like, you can say when you like, when the information goes away, because you can't have access to it anyway when it's in the black hole. So it's a matter of, at some stage, changing your mind about which phase space you use. You see, the entropy is defined in terms of volumes in phase space, and if you lose information, the phase space gets collapsed down along all those dimensions which get swallowed by the black hole. And you can still have an evolution which follows some specific curve in phase space, but it collapses down into continuing the evolution in the smaller phase space. So every time the black holes disappear, the effective phase space, the one that you would use in actual calculations for the entropy in the universe, when the black holes have gone, has come down. And so on this view, there is no violation of the second law, but it is in a certain sense, as Wheeler might say, transcended. The second law is only transcended because you've decided the old phase space isn't any good because it's got collapsed down to a much smaller phase space, and so therefore the definition of entropy that you're now interested in uses a smaller phase space, and therefore it's allowed to be a smaller value, and then you can come down to the value that you have, the low value you can have next. Oh yeah, I was going to show some pictures. Yeah, let me quickly say something here. I'm running myself out of time. What about observations? These are meant to be black hole. See, this is black hole collisions, so these are supermassive black holes now. I asked myself, what is the most violent process that I could think of, apart from the Big Bang itself, and that is the collision between supermassive black holes, such as when our galaxy runs into the Andromeda galaxy and our black holes finally spiral into each other. That will be happening many times in the previous eon, and there will be a great burst of gravitational radiation. Now that gravitational radiation will hit the crossover surface, and here I have a slide here which I'm afraid I can't go into in any detail, but this is how you start to do calculations, and you have the crossover surface here, and you use one metric before, one metric afterwards. Here, the way it works is that you have a conformal factor. You have to write your Einstein equations in a conformally invariant form. So you introduce the conformal factor. It's just a variable, another variable, and I call this a phantom field because it's not real. But the field equations, it has an energy momentum tensor. The Einstein field equations is that its energy momentum tensor is the energy momentum tensor of the matter. That's just the Einstein equations. And then when crossover happens, you have to change your conformal factor to its inverse. That's what you do here, apart from a minus sign. And then this thing becomes a real field. And this real field is interpreted as the initial form of dark matter. So dark matter, according to the scheme, is there. It's the companion to gravity, in a sense. It picks up the gravitational degrees of freedom. There will be degrees of freedom in the gravitational radiation, which get converted into degrees of freedom in the dark matter. And that will produce signals that we might see. And that's what this picture is meant to be doing, what you would see with the circular features. I hope I have time just to show a few slides here. Can I make this thing work by pressing a button? I just want to show the observations. See, all this is just ideas, but is there any observational support for it? I claim there is. And do I have to press a button to make this show up on that screen, or do I have to turn this off, or what do I have to do?
No, that's fine.
Oh, it happens itself? I just waved my hands. It does, yes. This is a picture of the cosmic microwave background analyzed in a particular way. So that's the whole sky. The gap in the middle is the galactic plane. So this is done, I should say, my colleague Sahi Gurzajan in Yerevan in Armenia. And what we were looking for are rings along which the temperature variation is lower than normal. This is because, you see, the black hole will, I won't go into the details of it, but you expect to see something where around the ring is meant to be, no, I've got rid of my other picture, but you have the collision between the black holes. Think of the crossover surface. It's a three-dimensional surface, so that could be this room here. And so you have sphere. That sphere is where the black hole radiation is hit. Another sphere over here is where we look back and look at the microwave background. They intersect in a circle. So that circle is the circle around which we expect the variation to be, the variance around the ring to be lower than average. Moreover, we expect to see, because if we're looking at one of these bursts, that would be some supermassive black hole sitting there which may be swallowing one and another, so it'll do it several times. It may be that in the same galactic cluster there will be several doing the same thing. And so you will see lots of these bangs going off, and they will look like concentric circles to us. So the idea here was to look for concentric circles. Perhaps I can get this thing to work. Yeah, I think so. Yeah, I can forward something. So we were looking for points at which there were at least 3 circles with the same center. And the circles, you can see them, sometimes they get very crowded, such as here. Now, we did all sorts of tests on this, and people objected because for all sorts of reasons, some of which were good and some which were bad. But we decided to have an analysis which was independent of all the objections, which was to twist the sky, just starting at the North Pole and getting the twist increasing as you go down, so that circles become ellipses. And then you use the same algorithm looking for concentric circles, and so these are looking for sets of ellipses instead. And so in the next slide, this is showing you, top one is on the left-hand side, is the centers, I think. No, I can't even see it myself. This is without any twist. Then as you go down the left column, the twist is increasing. On the right column, the twist is increasing, but in the opposite direction. And you see the more twist, the fewer circles you see. The circles go down, so it is a feature of them genuinely being circular. We see, I forget what the number is, 253 or something altogether, and the numbers of them drop. Then we did it for 4 concentric sets, and the numbers drop even more dramatically. So there is some feature which is definitely the circles. I should say that other people have repeated this analysis and found a very similar picture, so there's nothing wrong with the picture. This, I should say, is looking at the Planck data, and it's even more, the clumping is even more striking than before. You see far more of these centers because, well, anyway, I forget the number in this picture. I think what I want to leave you with, however, is the centers. If you plot the centers, and now there's coloring, you see they're very, very clumped. I hadn't expected them to be very clumped. However, this is quite plausible on the scheme, because it would mean that you're looking at regions where there are, with super-duper galactic clusters, with, in some places, lots and lots of supermassive black holes, and others not so many. And so that's why you get the clumping. However, how we would explain that in a conventional picture is very hard for me to see. I should say, what about the color scheme? Well, that's another feature which is independent, because we didn't look for the temperature, we just looked for the variance in the temperature. But if you now say, now you actually see what the temperature is, and how does that differ from the ambient temperature around? And the red ones are the warmer ones, and therefore, according to the scheme, blue shifted, and therefore more distant. It's complicated. But the red ones are the more distant ones for a double reason. The blue ones are the closer ones, according to the scheme. So we seem to have a very relatively distant, very, very distant region there, outside our particle horizon, in fact. And over here we would have a nearer region, and here something intermediate. So that would be the idea. How does the conventional theory explain a thing like this? I have no idea, but the sort of thing you would expect if you were just looking at some kind of conventional inflationary scheme where the fluctuations come about from quantum fluctuations in the interton field. You would expect to see something much more uniform, and the temperature is also much more uniform. So that's what one would seem to expect, unless there is some other reason that somebody can point up to us. But this is, I don't know, the wrong one. This is what we see. So we need an explanation for that. I think I'll stop at this point. Thanks very much.
Yeah, as I understand, part of the idea is your Big Bang surface is conformally invariant because of massless fields. But if you have gravity waves or gravitons from the previous universe, would those break the conformal symmetry?
No. Well, it's not completely uniform. I didn't have the I was running myself out of time. The gravitational waves, when they hit scry, they convert themselves. Well, you have a curvature. The normal derivative of that curvature is non-zero. Now that converts itself into a magnetic part with respect to the normal to the surface, and that magnetic part, as Paul Todd has shown, is the Cotton tensor. So it does give a non-uniformity to the intrinsic conformal metric of the crossover surface itself. The electric part goes into the kick that's given to the initial dark matter, the initial dark matter being supposed to be this new field that gets created every time it crosses over. So that's the argument, but the dark matter is a sort of accompanying field to the gravitational field. So we don't expect it to be uniform, no. It's just conformally smooth, that's all.
I have a remark concerning a more mundane aspect of your talk, which is the smoothness of stripe plus. You said you expected smoothness of stripe plus, but perturbation calculations show that in the case you were showing of a binary system coming from the infinite past, and the fact that I0 is a bad point, which means that you have tail effects with the Coulomb effects of the thing, reflects back the waves by the tail that go near I0 and then go along stripe plus. And these tend, at least in explicit analytical calculation, to show that stripe plus is not very smooth. I mean, it is like C0, but not more.
I think there's a lot of freedom in how you see, you choose I0. You certainly will get, I think from what you're saying, you certainly are likely to expect on square minus some tail of radiation going out like that, and that will affect the structure. But reflecting off I0, I don't see why.
Yeah, that's the tail,
Yes,
on
I think
curved spacetime.
as far as I can make out, the difficulty is at I0 of preventing some kind of shock wave or something up sky is encountered when you try to make both square minus and square plus smooth.
But here, maybe both of them are not.
And I don't think
are not CK for large K. That's what I'm saying. That both of them have a low. Both of them are C0 or less.
Well, I think you might have some choice as to how you do it, but I think it's an open question. But thank you for your comments, yes.
It's quite late, so thank Roger for very thought-provoking